Just let me, let's see, if it's not working that well, let's see if I do want to show you though, an example of what what that output is. So here I'm just taking that question, I'm just sending it to the LLM, and I'm just asking it to come back and give me the embeddings for that short string. By the way, even if I give it one word, it's still going to come back with 1,536 dimensions. So this is very computationally expensive. You'll have to you're trying to match this array of floating point numbers to a bunch of other parts of the system internally. So there's the 1536 dimensions that came back from OpenAI just based on that little query string, based on that prompt. So that's RAG. Components of RAG, as I mentioned, chunking the data, storing the data, embedding that data using different embedding models. The choice of model is going to be important. Which model is better than another model? Some models are better at certain use cases than other models. You know, how do I chunk it? The size of chunking, do I do overlapping chunking? Lots of different techniques there. Retrieval of the documents. It turns out that part, which you know, Couchbase does, and there are other solutions out there, you know, is relatively straightforward. I want to find nearest neighbors for that set of data. Then you know, being able to deal with the answers, as I mentioned earlier, you usually want to provide those chunks to the LLM in order based on how well they match. So the topmost matches are the best context, and the LLMs will tend to read that in order. You also, by the way, I don't think I actually mentioned that here, but you'll notice, scrolling around too much, when I was running that earlier, here I said neighbors 5. I said give me the 5 nearest neighbors. I could say give me the 25 nearest neighbors. Here's the thing. LLMs, if you're using OpenAI, will charge you based on the number of tokens they process. So the more context I give it, maybe the answer gets better, but it certainly costs more. It may or may not you know, actually get better. And in some ways, from a database or a computing perspective, this is kind of interesting, right? Because basically what we're dealing with here is something that is just not precise. It doesn't, it certainly is not giving you the same outputs for any given input. You could ask the same question multiple times and you're going to get different answers. And as far as whether or not that answer is good or good enough, that becomes a little bit of a challenge. You know, you can do things like chat with docs on RAG. So we have some examples of that. There's a question and answer bot demo that you can download, and you can just import. You can set up your Couchbase, or you can use Capella, which is the hosted version, import a bunch of PDFs, and you can basically build what Gemini have in the Notebook LM, but you can do that with your own data. And if you use the AI services that we have in preview, then you actually are never having that data leave that particular area that's just for you. You're not giving it to Google or OpenAI or anybody else. Still, there are some limitations. We're making it better, but we're retrieving a certain amount of data and putting it in front of the LLM, but the LLM is limited based on the context that we give it, limited based on how we do the embedding models. There's also a not unreasonable amount of cost of figuring out the embedding models and updating them as the data changes on a regular basis. So there are a few things that we'll have to consider. We do have, by the way, you know, some services that when you add documents to the system, we can just automatically generate the embeddings for you if you set that up as an example. That's one of the preview services. You can also, so a couple of recommendations here. Definitely measure the performance of retrieval augmented generation. So couple techniques for this. One you've probably already seen. If you've ever interacted with an LLM, sometimes you have that thumbs up, thumbs down. That's you helping them figure out if it's figure out their test cases, right? Similar to you know, Tesla collecting all of the driving information and then, you know, trying to weed through it and figure out what's good and bad. The vendors, or if you set up your own LLMs with your own applications, that thumbs up, thumbs down is really useful data, particularly the thumbs down. to turn into future test cases, look at new embeddings, look at new prompt, system prompt to help make that better. But the challenge there is that's very resource intensive. So there are test frameworks. Langsmith has some tools for this, and there's a project called Ragus that allows you to test lots of different environments. So if you were to have a small corpus of data and maybe a set of questions that are representative of the way that you want to deploy that application, then you can try OpenAI and this model, or Anthropic Claude and that model, or Gemini and this particular other model, and they all have different costs associated with them. And then you'll have to kind of figure out what's the best return on the investment for what I'm paying, what am I getting the best results for. Okay, so now we're getting into the more advanced stuff, dynamic agents powered by LLMs. So what is a dynamic agent? An agent in this case, unlike the last case where the LLM was, I'm just kind of building these metaphors on the fly, but in the last case, that LLM was kind of a research assistant, and you're putting a bunch of papers on their desk and saying, go find me some information in this, some additional context. In this case, you're saying, hey, I want you to go to the library and go find books yourself, and if there's nothing at that library, go to another library. I don't care how you, here's a set of tools, if you will, that let you solve that problem, and you're giving that to the LLM. So in that case, LLMs can react with the environment that they're in. So they're augmented with a set of tools, and that set of tools, they will be able to reason and then act on that reasoning. So they'll reason about what the task is, then they will go use that set of tools to try to answer that, and they'll call different tools as needed. And there are a few aspects to this. There are things called feature stores that have specific information for your particular environment. You'll have a metadata store that will have a certain amount of metadata, and then you'll put those tools in front of the LLM, and it can reason about how am I going to answer that prompt by using these different, by using a feature store, metadata store, and the other set of tools. So one more demo. This one, we'll see how it goes. Okay, you know what I'm going to do? I'm going to show you the answer first, and then we'll try to run it live since I was having trouble with the other one. So in this case, I ran just before we started here. Imagine you have a SQL, a Couchbase store, and it has SQL++. So I can go write SQL on it. Is that a request to make it bigger? I can go write SQL. There we go. Is that bigger? I can go write SQL, but not everybody knows SQL, or not everybody knows it super well. You might want to say, in the organization, like, here's a natural language query. You as the LLM, you know SQL. Here's the database. Go write that query for me. And you can even imagine with not too much more programming, you could say, like, go write that query for me, and here's some image generation. Generate some graphs for me, as an example. That sort of thing. So the one I ran earlier was, what are the best hotels near Griffith Observatory? And it went off, and I'll show you this over in the IDE. We'll try to run it, but since the other one didn't run, I'm not terribly optimistic it'll work. It went and ran select HName, HAddress, HCity, so it has a bind variable. It's going and finding all the things it needed from the hotel collection where the city was Los Angeles and state was California. And it wrote all of that on its own. To give you a sense of how it did that, I ran it in debug mode. So here, if we look back a little bit, you'll see things like this: infer airline. So that infer airline, what's happening is inside the database itself. If I were to go over to the query portion in Couchbase, so one of the great things about a document database is the schema is flexible. One of the challenges with the document database is the schema is flexible. So when you have that kind of flexible schema, you may need a way to understand what's actually in the schema. So as an example, I might run infer hotel And so there, infer is this keyword that will look at a collection and it will try to find what is the common, what are the common flavors of documents stored in this. Because it turns out, even though it's a document store, most of the data is machine generated or application generated, so there is a schema. Implicitly, each document has a schema, but you want to be able to understand that schema. So if I ran that infer hotel, I get this long response that tells me what are, for example, what are the different types of documents, what are the properties of the documents. They all, of a bunch of documents, they have addresses, they have aliases, they have check-in times, they have checkout times, city, and that sort of thing. Over in the app, what we're doing is in the collections schema, oops, sorry, no, not there, in DB connection and get schema. So we're getting the schema for the collections, and then we're generating the schema from the infer. So here I'm combining some techniques. This app was actually written by a colleague of mine, but basically he's saying system prompt, and then you're an expert at generating the schema from a collection of infer statement output. Generate the schema in JSON format based on the infer, return only the JSON and nothing else. So it's taking that big chunk of output. So what the LLM is doing is it's calling infer on all the different collections, sending that over to the LLM in context to get the schema of the system. So it doesn't know this database at all. It's never seen this database before. And then after we do the get schema, we're going to generate the schema output and generate a query. And so in the end here, you'll see generate a SQL++ query to retrieve data from a collection in a scope. You know what I should have done is I should have actually run it. Oh, wrong one. I don't know. What are the big... how about this? Give me the worst hotels near the Santa Monica Pier, right? So I'm writing a SQL query. So in theory, what should be happening over here right now is right now it's doing the lookup, getting connected to the database. Taking a little while. Okay, yeah, so it's done its database query. It's probably sent that off to the LLM. So you're an expert. Given an input question, generate syntactically correct SQL++, generate it with the tool call. This is all system prompting. Here's some of the guardrails. Don't make up answers if you don't really know them. Don't modify the database. Don't use any DML statements. The schema for collections is as follows, and this was based on what we retrieved earlier. And then return only the SQL++ query and nothing else. And this is just the portion that generates the query. Then we take that query and we go execute that query. The red is probably not a good sign. Host not found. Okay, the network is really not terribly happy. Sorry about that. So I will probably not get a response here if I'm getting host not found. It's going to keep trying. So this gives you a sense of how you can use an LLM in an agentic sense. And one of the things that we released recently that is a set of tooling written in Python is you can imagine inside an organization you're going to have a whole bunch of tools that you might want to put in front of LLMs in different cases to pull different tools in to solve a particular question. And each one of those tools might be developed, right? You have to kind of put some constraints around where that LLM goes. So you're going to catalog that set of tools. So that's what we have is we have something called an agent catalog. Because you can imagine I might have inside a company, I might have lots of databases, but I don't really in most cases want people going just straight after the database. I probably want them to go through a certain set of tools to be able to figure out how to get there. So agent catalog is one of the things that we've released recently for that and we're trying to move forward on. So that was an example where natural language, I was able to run a SQL++ query, get the results back. And I would tell you that it's really interesting playing with this. Earlier today, I did one. I was hoping I'd be able to do this demo. I said something like, find me the best hotel within 25 miles of Griffith Observatory. And it went and did all of the documents in the system have latitude and longitude for the locations. So it went and figured out how to use the cosine function and so forth to put basically a centroid and say rather than a bounding box. Most of the time the queries I get back are bounding boxes. This time it went off into trigonometry, and I didn't have to write any of that stuff. Right? I'm sure I could. And it might, it might take an hour or so, and I'd probably spend some time on Stack Overflow. But instead, it did it in about 4 or 5 seconds. Let's see if it came back with anything, really briefly, before we move on. Yeah, it's still working on it. Unfortunately, if it's hitting DNS issues, then we're not doing well. So in this case, what it did is it just did limit 5 and gave me the top 5. Yeah, this one wasn't all that great in some ways, because did I say best? I said best, and it didn't even look at the their ratings on these hotels. So it didn't do a great job in that case, but you get a sense of how that works. Limitations, workflows are potentially quite complicated, right? You're going to have to do all that system prompting. If the base model doesn't know how to do things, you have to give it lots of examples. And those examples might even be example queries. We're working on some techniques around that. It might need human intervention in certain cases. Do you really want to give, I don't know, if I'm a particular kind of company, do I really want to give everybody access to the database? Probably not. Usually you'll wrap that up with an application of some sort. But there's some great things that you can do. You can combine agents with RAG. So you can have an agent go off and do queries, and then you can do augmentation as well, plus all the system prompting that I mentioned earlier. Just in conclusion, a lot of great tools. The world's moving really, really fast. There are some great opportunities here. We're now in a state where whether it's Couchbase or something else, you can take a lot of these open source platforms, things like LangChain, things like Llama Index, things like Haystack, things like the part about guardrails, and assemble a really great solution for your kinds of applications. And you can do that with your own data in your context to really help, whether it's your end users internally or whatever you're doing as an application to maybe a research environment or something like that. Great UX, consider privacy, and consider how you're going to test and improve these sorts of things over time. All of the demos I showed, Couchbase Shell, those are all available. These will be in the slides, of course, which I'll provide later. And as mentioned really briefly, we do have a set of AI services, and we're contributing into a number of the open source projects as well to try to make them work better with Couchbase. So if you're interested in any of that, by all means, sign up for the AI services preview. So I'll leave that on the screen, and I think we're set for questions, if anyone has any.
Do you have to be concerned about injection attacks?
Injection attacks? I mean, with SQL, and that is a general problem, if you will. There are normal techniques, if you will, for that, bind variables and that sort of thing. But obviously, if you're agentic-wise putting things together, you're going to have some concerns. I don't know how better to answer that. I mean, because there's sort of the part where you're hijacking especially in a case where I've given an LLM some agents, some tools, and now if I hijack it to ask nefarious questions, yeah, you'd have to be concerned about that. I would agree. And those tools may not, it might be there's a database in the background, but some of those tools might just be calling other REST microservices or something like that. So you'd have to be worried about that as well. Yeah. Next.
Excuse me.
Did you consider also fine-tuning for faster response or for better, like better, better use of your compute?
Yeah.
Going over the
Excellent
same
question. Excellent
data.
question. Yeah, so with LLMs, you can use an LLM out of the box, and the weightings, all of the training that LLM has are basically fixed, and so we're just kind of layering on top of it. And the question, in some ways, is have we considered fine-tuning? I will be honest, that's a debate that we have internally. There are a couple of people in my team that say, in the future, people are always going to be fine-tuning and creating their own models. And then there are other people that say, RAG and agentic is good enough, why would anybody bother with that? It's so computationally expensive and you're going to have to redo it. What we're doing is we kind of expect that it's going to be probably context dependent. There are cases where people will want to do the fine-tuning, adjusting the weight of a model. So for those that don't know, Llama in particular, Facebook, or Meta, I should say, doing lots of work in open source, you can use that as a base and then kind of extend the model from there and do additional fine-tuning on models. So I don't know what the answer is. We're kind of prepping for people to do both. In some ways, I liken it to what we want to do is be providing tools to the people that are exploring here, kind of selling pickaxes to the miners. So your choice as to whether or not to do fine-tuning or use something like Bedrock or Gemini or OpenAI. Hope that helps.
Question. So you said maybe, I guess about a year ago, 8 months ago, all the brag was about RAG, and now it's not necessarily as exciting. So this question kind of touches upon that. Both the SQL generator, LangChain agent, let's call it, and also the RAG, that's been pretty mature technology in open source for almost probably a year and a half, but the adoption has been terrible. Why? What happened?
Why? What happened? Oh, I think you're asking a sociological question, which is really hard to answer.
Well, I mean, as somebody who's in a company doing this.
As somebody who's
what
in
are
a
the
company
trends?
doing this, and as somebody who's been doing this at least since the late 90s, like the metaphor I would give you is, if you think back to the late 90s, we thought like, oh, the future is going to be the internet, everyone's going to put things online. Initially what we did is we did like online brochures. And then after that, we took like input, and then there started to be stores. But really it took about 20 years for all of that, and we had some economic up and down in between. And so I will challenge you, as soon as you think of this idea, please come back and let me know, and we'll go do a startup together. But the people that really made the internet take off were the ones that weren't trying to take the real world and put it online. They were trying to figure out, how can I leverage this to do something that I couldn't do before? So think of like early days eBay. It was suddenly consumer to consumer auction, right? You couldn't really do that without the internet. Modern world like Uber. I remember late 90s, you would like make up a fake name and email address because you wanted to hide your identity on the internet. And here in 2025, you actually summon a stranger to pick you up at your house. So things have. So I think with these tools, yeah, it's wavy. My own personal opinion, but I think I remember one researcher putting it this way: the Industrial Revolution let humans do things that they couldn't do with their own bodies. The AI revolution is going to let us do things that we can't do with our own brains. So as soon as you have that multi-billion-dollar business idea, let me know, and we'll talk.
Yeah, I have two questions.
Sure.
The first question is connected with your text embedding model. So I have difficulty finding the best embedding model for my RAG application. Did you find out a best embedding model depending on the embedding dimensions and things like that to give you the best answer? Because the answer is probabilistic, so it's very hard to figure out the right one. The second question is regarding the AI agents. When you run AI agents, it's actually running Python code on your laptop, right? It's running Python code on your laptop. Some of the agents can do that.
Yeah.
So it could potentially damage your whatever is there. So did you consider sandboxing and things like that? Okay, that's two questions.
Yeah, two-part question. I'll try to make sure I repeat it. First question was sort of like which models, which embeddings generate the best results. In my experience, both working with end users and with our own internal tools, is it varies quite a bit. So one of our summarization tools, we found that a particular model from Claude was much better than one of the OpenAI models that we started with. And how do we know? Unfortunately, it's experimentation. But we have been, on that particular project, the person on the team's been working with Lang Smith as a way to evaluate lots of different systems. And here's the challenge, is we're gonna have new models that are gonna come out later. So we're probably gonna have to change it over time. Second part of the question was, really, in some cases, those tools might be running here locally on my system. And do I want to, might I want to sandbox that environment in some way, shape, or form so that it can't it can't accidentally be hijacked to cause some sort of damage? Yeah, I think that's a very, very, very valid concern. And as a matter of fact, with the Capella architecture, part of what we do is we segment deployments into separate VPCs. So as an example, we anticipate that as an end user, you might actually have an environment that has a certain set of data, but it's completely segmented from another environment. That helps a little bit. I think we're just at the early days of figuring out what those constraints are with the catalog. My own personal opinion is I think we got to get, as an industry, we got to get a lot better about the how do we pass the identity context along so that we can know what the access controls should be. Like, should this person be able to access this database? The browser prompt is very removed from the agent. We got to pass that context down, and there are techniques for that. Two more questions. Yep.
Thank you. The rule of thumb for the other question is that it takes 40 years for a serious invention to soak into the economy. So keep up the hard work.
Exactly.
Thank you very much.
The future is here. It's just unevenly distributed, right? Last question, and I'm here all day, so I'll be happy to stick around. And my colleague Nitish, he's doing a demo later this afternoon, some talk. Yep.
Thank you so much for the presentation. And I have a question regarding the vector DB. Is that the purpose of caching the query in order to boost the performance, or for the fine tuning for later use case?
I'm not sure I caught the first part of the question, but I definitely caught the part about caching. So I think is the general question, how do you improve the performance,
Yeah, what is the purpose of using vector DB? Just instead of sending embedding to the model directly, you have the intermediate layer of vector database and the search.
Oh, well, yeah, you could certainly, so in some ways the question is like, can I just go use, instead of getting the embeddings from the model and then using that to do my vector search, can I just go do my vector search directly? So kind of two answers. One answer is, in my own personal opinion, like vector database has been around for a while, but vector search kind of took off for this RAG case. Suddenly now lots of other people are hearing about it. Second part of the answer, though, is I actually anticipate that there might be some situations where you might run a local model for generating the embeddings on the question, because you can do that with kind of a fixed cost, really low latency. It's basically on a machine sitting here right next to your application. And then you might use that, maybe agentically, you might choose to use it against another model. But yeah, there are lots of cases. It kind of comes down to, do you want a fixed cost around it? But there are also techniques like semantic caching for being able to understand when a question comes in, have I already seen that question and answered that question? And then I just use the same answer as an example. And then in this particular demo app, I wonder if it actually ever finished. In this particular demo app, we probably should be able to, oh, it did. It ran, okay. So in this particular demo, oh, and actually, check it out. Unnest H reviews were latitude is between this, so it built a bounding box. Like, so it figured out on its own to build a bounding box. But every time I make that request, it's doing an infer against every one of the collections, sending it over to the model. We should be caching that, basically. All of, another way of putting it is like everything that you've learned about software development and system development is still valid. So, with that, thank you very much. Appreciate it.
Thank you, guys. We'll be back here in 15 minutes for the next talk.
Oh, yeah, I can do that. Yeah, no worries. Sure.
Testing, 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 testing. Can anyone hear me? Yeah? Can you hear me in the back? Is it still a little low? All right. Oh, on here? Yeah. Wait, how do I raise the volume? Oh, that says menu. Oh, all right. I'll try this. Hold on. I know. It doesn't look like this raises the volume. This just changes. It's a. That says IR, and that says menu. We're just trying to raise the volume.
We have to do it over here.
Oh.
On the board, I just want to see which.
Oh, it has to be done there. Okay. She said that people have been complaining about not being able to hear in the back.
Okay, perfect. Let me find out.
Hello? Testing, testing.
I think the best.
Testing, 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 testing. Can you guys hear me in the back? All right, cool. Yep. Yeah, yeah. Maybe a little bit lower. I feel like I'm getting feedback, but overall, pretty good. Testing. Yeah, it's good. Thank you. Yeah, I think so. Yeah. Okay. Thank you. I'm trying to do that now. Yeah, let me see if I can get this going. Here, I can do this. I think I can just go like this. Is that visible? Oh man. Wait, that's not even. Yeah, it's the wrong one. Hold on. I don't even know what that was. Hold on. Hold on. Let me try that. All right. All right. So. All right, let me see if I can mirror this real quick. Okay, cool. Let me see if I can get my phone going. Yeah. It does not look readable. Hold on, it doesn't look readable there. Oh, okay, cool. Um, yeah, yeah. Sure, if you want to. Yeah, that's fine. At the end's better, yeah. Because I think I'm going to run out of time.
Welcome, welcome to our second day of SCaLE 22X. Next, we will have Mr. Masahi Stewart. He will be presenting his talk, Next Generation Prompt Engineering, Building Scalable, Cost-Efficient AI Applications for Multi-Model and Open Source Environments. Please hold up your questions till the end.
Thank you. Okay, thanks. All right, just a heads up. Last night, my sinuses exploded, so just in time for the talk, so you might hear me sniffling a little bit. So you may have noticed in the talk on the description there was a small change in the description of the talk. It's still next-gen prompt engineering, but it turns out that this talk is going to be about a lot more than that. And it's really about code generation, prompt generation, and generally problem solving using large language models in an automated way. So what a year. I know that probably triggers a lot of things for different people, but it's been a crazy year for AI. You know, last year and even now, there's been a lot of excitement. I would say it's the excitement. Oh, you guys hear me? Okay. I would say the excitement has become kind of now becoming more of a. It's getting mixed with a little bit of fear as well, and I want to kind of address that as well. But it started out with excitement, and it's usually how it starts with most organizations. You know, a lot of folks, they're looking online and they're seeing, or I don't know who reads the newspaper, but they're looking online and they're seeing all kinds of articles about robots, AI, are they taking our jobs? And then, of course, you get this kind of cover, and after a while, everything these people say suddenly becomes the gospel at whatever organization you work for. So everyone starts out with big dreams, wanting to do stuff with AI. Companies dream of using AI for basically everything. We'll replace our customer service. We'll have developers that will be AI coders. We'll have AI product people. We'll have in fact, our whole business will be AI. In fact, you know what? Maybe we'll just rename the business to whatever we were doing, and then we'll put AI, and in everyone's title suddenly has AI in it as well. And leadership gets inspired by big talks from industry leaders like Sam Altman. And you know, that's the overall feeling is we got to get on this train. It's the way of the future. And it really is, but I think that there's a lot of it is not really rooted in actual knowledge of what these systems can do and why what we do is actually really important as well. It's also, a lot of it's rooted in just the hype. I mean, what people are talking about. Everywhere you turn around, people are talking about AI is going to do this and AI is going to do that. So, of course, everybody's organization is in constant meetings about AI. They're having war rooms and groups talking about AI, and you know, it's warranted. It actually really is important. So, of course, this always falls on the engineers. At the end of the day, we've got to build stuff. So everyone's in a room talking about all the great things it can do, and then it's like, well, let's make something. And so, of course, what does the natural engineer do? They start looking at everything. They start looking at large language models. Maybe before that, they even start looking at how neural networks work. They start seeing if they can train their own neural networks. They start looking at fine-tuning. They start looking at embeddings, classification. They start looking at statistics if they don't have a background in that. And they look at all the models and all the different tools that they can use. And it's just a lot. And everyone wants to do something now. And that's generally how we feel, especially when it's like, okay, well, what can we do next week, right? And so what do we end up doing? We end up sort of settling on the practical frontier models because they work. You can just get an account, go on OpenAI, get an API key, and you can start coding. You learn about tool calling, you learn about embeddings, you learn about RAG, you learn about all kinds of useful things, and you start making things. Of course, people look into Claude. That seems really cool. So maybe we can switch out models. Okay, maybe I need a framework. They start looking at LangChain. And of course, that dolphin shows up. And people are wondering, what's that dolphin about? And then, of course, OpenAI releases O1. And it's like, okay, well, what about these reasoning models? How does that work? How does that change things? And then you've got 3.7 Sonnet. It kind of seems to do lots of interesting, lots of good work around coding and problem solving. And it's expensive. And then DeepSeek R1 comes in and says, okay, well, actually, anything you can do, I can do better. And it's free. And so people start looking at the statistics, and it looks really amazing, but then what does it mean to us? So it's time to start building. What do? We pull out LangChain or Light LLM. We start doing tool calling, RAG, like I mentioned before. We look at a lot of the different tools, and we start getting early results. This is where the excitement happens as an engineer. We start doing demos. We create a little AI assistant. We plug it into some data from our organizations, and things just sort of work. It's kind of magic, actually. It's really amazing. Why it works, no one can tell you, but it works. You just put a prompt in, you put some data in, and it seems to come back with the answer, sort of, and sometimes better than what you expected most of the time. But then sometimes you get stuff like this. Wait, I thought we made 13 million, or the forecast was 13 million, not 12.4. Where'd that come from? Now, of course, everyone sees all the output and is really excited. The organization's excited to actually keep building. But the engineer inside of us, the engineer who's actually working on this, inside our heads, we're thinking, that was wrong. That answer was wrong. And now I have to kind of do something about it. I don't know what to do about it, though. So it's time to start thinking about releasing a product. And then the engineer's thinking, how do I know if this is even going to work? Well, QA will find the problems, right? You just throw it over to QA. They're going to run some tests. And we did it. We released our part. They're going to test it. And you know, they'll make sure it's OK. But just put something together to get people excited, because there's just so much pressure to build things with large language models. So this is what we feel. So we start to abandon our principles about verification, about testing. We start to kind of move away from that and just sort of trust things, because it seems to work most of the time. But something's amiss. And we start running things on our own, and we start asking other interesting questions. And we start discovering, wait, there's no membership. There's no membership program. Where did it come up with that? Wait, we don't have patents. Why is it talking about patents? So of course, with all the big dreams that everyone has about, organizations have about building all these interesting things with AI, what ends up happening a lot, and this is what we've noticed at Singtree, is a lot of people end up settling on, why don't we just build a chatbot? Now, why do chatbots work? The reason why they kind of work is because generally, chatbots are, the interfaces with humans. And the large language model has been trained on mostly human input, human text, of course code as well. And so what's great about a chatbot is the user gets to fix the errors. The user chats with the chatbot and it says, oh, that's actually not right. Can you explain this or explain that? And they're sort of correcting the problem. But if you just build chatbots, it's actually a pretty limited use of large language model. So of course the engineer is pretty frustrated. You know, I thought I could build all these things, but now I'm just building a chatbot. So let's talk about what prompt engineering actually is. So, you see all the errors, you see all the problems, and you start thinking, I can fix this, right? I can do this. So naturally, the engineer creates a prompt. The large language model processes the prompt. The model generates output. The engineer evaluates quality. Sometimes the customer or sometimes someone in in the company evaluates quality because they're playing around with it, and they say, hey, I entered this thing, and it entered this input, and then this happened. What's going on? Can you fix it? And of course, they try it. An engineer tries it on their own, and it doesn't do the same thing. The engineer, if they can see it, they'll identify issues. They'll try to judge the output. And after that judgment of the output to determine, okay, this output is more or less accurate. If there is a problem with it, the engineer modifies the prompt. That's what we do. We start kind of monkeying around with the prompt. We add stuff to the prompt. We just start adding lines to it. And if we wanted to think a little bit harder about a problem, we use things like chain of thought reasoning. Think step by step. If we wanted to never do something, we'll put in all caps, never do this, and hope that it works. And we start to ask ourselves, is prompt engineering the new coding? You hear about people talking about that. Is prompt engineering coding? Is this the way we're going to do things in the future? But as an engineer, I think anyone who's worked on this can probably understand this. It feels like when you're doing it this way, you're just chasing a ghost. You're actually not really solving anything. All you're doing is you're sort of trying to influence this thing that you don't even understand. You're just putting text into this prompt and hoping that it comes back with better answers. And even the people who created the models could not tell you why it answers the way that it does when in very specific cases, because no one actually understands what's really going on in the model. It's not a program. I mean, you could say it's a program, but we'll get into that in a second. So it just feels wrong. But we do it because it's working, kind of. It's kind of magic at the same time. And then we mess with it, and guess what? It starts working. So you get it working, and what if you change the model? What if there's an announcement, and you've got to try the new model because the new model's better at certain things, and you've got a bunch of different prompts in your application, and you start changing things. You start manipulating the model. And when you do that, you start noticing that there are problems that start to pop up in your application. It doesn't work the same way. Maybe it works most of the time, but then there are situations where it doesn't work, where it used to work. And no one can tell you why that is either. Because just because OpenAI releases or Anthropic releases a new version of their model, it doesn't mean, let's say it's 4 and then 4.0, it doesn't mean that 4.0 is backwards compatible. It's not the same thing. It's a completely different model. And even if it was built on the same model, it's been retrained, or it's been fine-tuned, or something like that. It's been messed with internally, and even the creators could not tell you why it does what it does. Let's say the requirements shift. You want to change things. How do you deal with this? And as the models, or as the prompts get more and more numerous, you end up with a lot of issues. And of course, you end up with cost concerns. What happens when the models aren't doing what you want them to do? What does everyone do? They just put a better model on it. Okay, we were using 4. We were using 3.5. Okay, no one's using 3.5. Okay, we were using 4, then we use 4.0. And then actually, you know what? Maybe we'll use Claude 3.5. Maybe we'll use 3.5 sometimes, and then we'll use 3.7 now. And generally, what will happen is people will just keep dialing up the cost on the model in order to get better performance, so they just kind of hide the problem away. But it doesn't actually make the problem go away. So is it really good enough to go to prod? That's the question I think we have to ask ourselves. So of course, you get an announcement from Google I/O. They're going to have the Google I/O conference, and then immediately OpenAI does Dev Day just a day before the Google I/O conference, just to rain on their parade. And of course, that dolphin comes back again. So what's the problem? It's determinism versus non-determinism. When you are working on a computer program, you are working in a deterministic environment. You are building something that does what you expect it to do every single time. Generally, given the logic that you've put into it, you're writing a program. And I know for those who are into, computability theory, they might say, well, models are not non-determined. They are deterministic. You can turn the temperature down, you can run it again, and it'll give you the same thing. But whenever you have this massive, hundreds of billions of parameter neural network, and you throw an input into it, and it just goes, and out comes an output, that's non-deterministic. Like, I don't care what you want, how you want to, for all intents and purposes, this is non-deterministic. And so this is why this feels wrong, because we're trying to create this deterministic process, or try to create this deterministic expectation around something that is inherently non-deterministic. So some features of determinism. You have a pretty inflexible interface. You have your code. Your code takes a specific type of input. The behavior is predictable. It's reproducible. Its logic flow can be traced. Testing can verify all possible paths. Classes of errors are fixable with specific changes. So what's nice about that is you can say, okay, I'm noticing that I'm getting this error when this happens. I can handle that case, and it handles the entire class of problems that are related to that particular error, and you can bank on that working out. And that's why we can solve problems so quickly in code, because after a few logical updates, it sort of all makes sense. It all sort of works. And we as engineers have complete control over that. Neural networks are a little different. You have these hyper-flexible interfaces. You can put anything in there for the most part, whatever types of things it's been trained on, but it's pretty flexible, especially large language models. But the results can vary as far as what you think should happen, depending on the input. And you can have similar inputs and get different results that sort of break what your logical understanding is, because it is not a logical system. And when you run it, it's sort of revealing like probabilistic results. You throw a bunch of stuff into it, and you expect the output to be over there, but it's over there. And you expect it to be over there, and it's over there. And so engineers have no control. We can only nudge through the inputs or retrain. So what do we do? So one of the things that we've told ourselves at Synctree is that we'll never fully trust a prompt, ever. We'll never write a prompt. We'll try to never write the prompt, actually, as well. There are some edge cases to that, but we try to never actually write the prompt. We prefer to use hard constraints, things that we expect, be very clear about those, and let statistics be our guide. And we'll rely on automatic verification, and we'll watch out for overfitting, because we're going to train prompts, and we're going to train code, and we're going to train configurations, and that's what we are going to try to do for everything that we build now. Instead of building things by hand, what if we could just train everything and use statistics to determine if the system actually works? So instead of treating an LLM like a computer program, like a deterministic system, let's treat it like what it is. It's a non-deterministic system. Let's run a bunch of inputs on the system and see what it comes out with and get back a probability that it gives us what we want. So I showed the flowchart earlier about human-generated prompt engineering. So engineer creates a prompt, LLM processes the prompt, model generates the prompt, engineer evaluates the quality, output is it acceptable or not, engineer modifies the prompt, and we just do this loop. But what if we can make that automatic? What if instead of manually going in and manipulating the prompt, adding another line to the prompt. What if we can make it do it on its own? So there are a lot of little decision-making processes in here. We've got the engineer, of course, typing something into the system. The engineer is judging the output, and the engineer identifies whether or not the output's good, and then the engineer modifies the prompt. So what if we could use large language models and a combination of different models, if we want to actually do that automatically, and then use statistics to determine how good the output actually is, or how good the prompt actually is. Because love it or hate it, the prompt is still our interface to the large language model, and love it or hate it, the large language model is pretty cool. It is pretty amazing what you can do with large language models. So this talk is not about this paper, but it is a lot of what we've done at Singtree has actually been very much influenced by some ideas from this paper. I highly recommend checking it out. It's called TextGrad. It's a great read. It'll really change your mind about how you think about prompt engineering and coding in general. It's actually it's a great paper. There's an open source project around it. I highly recommend checking it out. It's done by a bunch of students at Stanford, and really what it's about gradient descent, but with prompts. In fact, let me go back and I can show you. Whoops, I didn't mean to go that way. So this image that you see on the upper right-hand corner, actually, this describes, on the left, you'll see a diagram that describes backpropagation, and this is how neural networks are trained in general. And then on the right, there's sort of an analogous process that we just talked about. That this is kind of a more mathematical formalization of that idea, but basically, as you see on the right, you've got your loss, which is really what's wrong with the output, right? It's the error. And then you've got your loss over your response. How could the output have actually been improved? Like what would I have liked it to have said? And then we then pass that, and this is what we do as humans actually. And then we pass that, what I would like the model to have, or what I would like the output to have been, we pass that to something that's evaluating the prompt. And there's a prompt evaluator that says, well, based on what I would have liked to have come out and what the prompt actually says, I think we could modify the prompt in this way. So it's kind of like backpropagation. It is like, in a way, it's like gradient descent, actually, if you actually keep running it in a loop. So let's make something. Let's do some prompt generation from scratch. A lot of what we're doing does not involve TextGrad, but like I said, it's a great project. But I recommend people actually get in and try to do this yourselves. Try to start from scratch and build something. So let me switch over now. Let me check on time. Okay. So let's get started. So let's come up with well, I've already planned this, so of course I know what the problem's going to be. We'll create a very simple system that answers questions about an article. And the goal is for the questions or the answers to create a prompt such that the answers that come out of the large language model and prompt together will be only things that refer to the things that are in the article. And we want to do this as a general thing. We're not going to say specifically for our particular type of article. It's just going to be any kind of article. So, given internet connection, I may end up I may end up walking through code rather than running, but we'll see how it happens. So let's get started. So the first thing I want to do is I want to generate an article. So let's start with that. So, excuse me? Oh, I'm sorry. Oh man. Is that good? I wonder if I could brighten it. Let's see, is it gonna do it? Yeah, the screen's resolution isn't great. Okay. Okay, let's try this. Yeah, it's gonna really throw off our, how everything lines up, but we'll try. All right. So I'm gonna generate an article. I'm gonna just create a simple Python function. It takes in a topic. It's going to return a string, and it's going to. We'll let Copilot guide us as well. Why not? Given a topic, generate an article. Sure, and then we'll. Oops. Sorry. All right. What's up? Okay. Here we go. All right. So I'm going to create a little prompt, and the way it's going to work is it's going to say, yeah, sure, that sounds pretty good. Generate an article. Okay. Markdown format. How about each paragraph will need to be, prefixed by a section. Yeah, that's good enough. And then we'll return. I have this little function called simple prompt, so mostly for this talk, so that we can avoid a lot of the inputs. Oh, you know what? I'm going to go ahead and create the article model. Yeah, like a little string that represents our article model. And I'm going to use GPT 4.0 mini, okay? All right, simple, yeah? And then what I'm going to do is I'm going to just log this thing out. So I'm going to say generate an article about, let's say, the SCaLE conference. Okay. All right, simple enough. So we'll start off with some articles. Let's give this a run. Hold on. Keeping some notes here so I don't get off track. All right. All right. All right. Easy enough. Up. Hold on. Let's try that again. It's throwing off my screen here. Let me just try to make this bigger so you can see. Okay. All right. So there's an article. Easy enough. All right. So let's take a look at. Let's take a look at what to do next. So now I want to create a some kind of program that will take the article and a question and will answer the question, right? That's how we start usually, this kind of thing. So this should be pretty easy, right? We just answer question, prompt, a question, and an article. All right, given a question and an article. Sure, generate an answer. That's good. That's a good enough doc string, I think. And we'll just return simple prompt. And, oh, you know what? I should do, Copilot knows I've done this before, so it's kind of guessing. We'll use 4.0 mini as well for the answer model. Yeah, let me switch. I'll try to like switch around. I didn't expect the resolution to be this bad. Okay, all right, and let's see. Oh, I'm like, what am I doing here? Okay, hold on a second. All right, let's try again. Let's do it like this. And you know what, I'm going to take this off because I can pass its parameters, and then I'll just do answer model. Yeah, looks about right. All right. Let's remove that. It's guessing. Okay, there we go. Yeah, okay, yeah, sorry, okay. I might just abandon this live demo just because it's because of the text and the screen situation. But basically what I'm doing is I'm essentially creating a, I'm generating an article, right? So generate an article about the SCaLE conference. Actually, that's here. And then what I'm going to do is I'm going to answer a question about that article. Okay. All right. Sorry, say again? Oh my gosh. Yes, I think yeah, it's this, because I can't see, Erilyn. All right, let's try this again. Thank you, by the way. I think I'm going to do it like this too, because why not? All right. All right. All right, let's see how I get back to my terminal. All right, so let's give this a run. What's that, Mark? Thank you for that. Good to see you again, by the way. All right, here we go. Okay. So I have a couple of recordings from the previous runs, just because I was having some internet connection issues as well. So, what is a SCaLE conference? Answers the question. Tell me about the latest iPhone. And I'm sorry I can't provide information about the latest iPhone. Now, what would happen if we change the answer model to something else? Let's use, I believe it's called, let's see, what do I have it labeled as? Hold on, I have a note on what I'm labeling it as. Yeah, 2.5. So Quinn is a large language model that was developed by Alibaba, and they have it actually performs pretty well. And there are some distillations from DeepSeek as well, and it actually turns out to be a nice little tiny model, but it hallucinates a lot. In fact, let me show you. If you've never run Ollama before, hard to see here, but all right. So this is a 1.5 billion parameter large language model. Runs on my laptop. I can call it as many times as I want. I don't have to pay for it, and I can talk to it, similar to how I might talk to GPT-4o. It doesn't support tool calling. But you can kind of make it work with tool calling if you do your own thing. But it doesn't have that built in. But it may not be good for, so as you see, it doesn't know what the SCaLE conference is, but maybe we could tell it about it, and it would be able to answer questions. Okay? So I'm going to jump ahead a little bit. Give me a second. I'm going to just speed this up and kind of prevent some of the issues. I'm going to go ahead and jump ahead and show you. Give me a second. I have a backup of the original. I'm going to just do this because I think it would be more, given how hard it is to see everything. I'm going to show you guys what it looks like. And we'll just review the code and I can just talk through it. It's probably better. All right, so this is actually the completed version. I'm going to review this with you, and then we'll actually run parts of it. Okay, so we're answering questions, right, as we saw earlier. And then what we wanted to do is we wanted to evaluate the answer. One of the things that we noticed is that when we ask Quinn questions, and I believe we have a run here that I can share with you. Whoops, hold on a second. Here we go. Jeez. Okay, so let me kind of show you what's going on here. So we created the answer question function. We have our prompt, we have our answer model, and what we did was we went through our collection of answers and we decided to start to evaluate the responses, because what we noticed was that Quinn was actually giving us back hallucinations. It was making stuff up. We asked it about the iPhone, and it was just making things up about iPhone sales when we were talking about the SCaLE conference. So we wanted to try to figure out how could we use the Quinn model still, because it's cheaper, it's really fast, I could run it locally, and it's just a good example of a really cheap, not very good model. How could we focus it to do something useful? So, and also exercise this process that we talked about of text gradients and backpropagation. So we created a pydantic model that essentially describes an evaluation that we would expect from a large language model. Now, in order to do this, you're going to need to have you're going to need to run this on a model that can support tool calling and a model that can actually adhere to a schema. So usually the models that are going to be doing the judgment of outputs, that are going to be editing prompts, are going to be more on the frontier model side of things. But ideally, that's really mostly where you'll be using those. You can also use this process for a frontier model to judge itself, to judge another instance of itself and improve its own prompts. So it doesn't mean that it has to be teaching a weaker model, but we're using this as really an illustration here. And then we tell it about this concept of error. What I want you to do is I'm going to give you, for a question and an answer, I want you to give me the error, and I want you to give me the reasoning for the error. So remember, that was that loss function that we talked about earlier, where we look at the output of the model and we judge it. This is what a human would do. A human's going to look at the output of the model and they're going to say, oh, this could have been better in this way. So this is the evaluation model. And then we have a function to evaluate the answers. And it's actually quite simple. Hold on. So here, if I can show you a little bit there. Okay. So, evaluating models or evaluating the response is actually really, really easy. Now, there are little tricks when you get more complex and you start doing code generation, things like that. But for the most part, it's pretty straightforward. You just say, hey, given my problem and this solution, tell me what you think about how good the solution is, and give me a reasoning, and judge between 0 and 1. And believe it or not, actually, that concept is pretty well understood by most frontier models. And so we implement this evaluate answers function, and then when we implement evaluate answers, we get this back, and I'll show you, because we have a rerun of it. Okay, here you go. So in this situation, what we're doing is we're throwing a bunch of questions with an article about the SCaLE conference to our model. This model is Quinn, the Quinn 2.5, 1.5 billion parameter model. And then we take the output of Quinn, and now we're judging the output with 4.0. And so you can see it answers a question about SCaLE, and it says, hey, this is perfectly fine, and its reasoning is the answer accurately reflects the information provided, and so on. But then we ask it about the latest iPhone. And when we ask it about the latest iPhone, it says, well, the most up-to-date information on the latest iPhone is that they're part of the 2023 lineup, however, specific details, blah, 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 blah. And I specifically told the model, or told the prompt, told the model through the prompt, I specifically said, don't make up stuff. Just give me back things that are based on the article that I provided. So 4.0 takes a look at that and says, that's wrong. So the error is 1. And since the error is 1, of course, it's going to give a reason, and the reason is the question about the latest iPhone cannot be answered based on the article, which is solely focused on the SCaLE conference and does not contain any information. So now we have our loss. So what we're holding here on the right is the output of the loss function. Evaluation is basically our loss function. So what do we do? So what do we do with our loss function, or with our loss? Okay, here we go. We want to try to start adjusting the prompt. So we take our loss, our evaluation, we pass it into another call to the large language model. We say, given this, what our goals are, given what we saw happen, tell me how we could improve our prompt. And I want to say the other thing about this whole process is that data is your friend. You want to be able to do this a lot. You can't expect it to just sort of work after 1 or 2 tries. You're going to have to pour a ton of data into it, and sometimes what's really useful is synthetic data. One of the things that we've been doing is we've been sort of making up data based on data that we already have. So we'll take a bunch of, like a corpus of similar data, and then we'll just generate a bunch of data similar to that, and then we'll use that as feeder data into our training process. So here's the adjustment model, or adjustment, this is the adjustment prompt that calls the model that we're using for adjustment. And really it's quite simple. This is a prompt with the highest score so far. We just do that because that way it has a reference of how good it's done before, and just in case it starts going off the rails, it can kind of like pull itself back. We've noticed that that's been a very useful thing to have that in context. So given the following prompt, adjust the prompt to fix the following errors. And the errors are the losses that we collected in the evaluation. Do not overfit to specific errors in the example. So overfitting is really about, if you're training a model, traditionally, if your model is just sort of mimicking the outputs of your training data, or mimicking the expectations of your training data and is not generalizing, then you're basically overfitting. So we don't want to overfit, because, so what does overfitting look like here? What overfitting looks like is a bunch of data that's going into your prompt with special cases for everything that we've seen before. And we've actually seen that before. So we've noticed that if we tell the model, don't overfit, we're going to try to generalize the problem, it actually does work quite well. And by the way, you might say, well, aren't you like writing a prompt to write a prompt? And you said don't write prompts. Yeah, I am actually. I am writing a prompt to write a prompt. But actually what we do internally is we train these too. I'm just showing you how to do it manually, and just to kind of get started. Okay, so we pass it through and we get a prompt adjustment. And I think that, let's see, I believe, let me see if I have a rerun of this one as well. I can show you. Okay, actually this is the main run, and I'll show you that. So in order for this to work, we're going to need a lot of topics. We're going to need a lot of questions. So we have a question generator, which is similar, you know, just pass an article in, give me some questions. It's really convenient for these kinds of things to use a frontier model where you can do tool calling, and also where it will adhere to a schema. It just makes everything so much easier. But don't let that dissuade you from using weaker models or models that are non-frontier models. With tools like this, you can technically use those models. Just I wouldn't use it for training. It's just, we found that it's just not practical. Although, DeepSeek R1, the 30 billion parameter model, we did run those, we ran that model on RunPod, and it worked really, really well, actually, and we swapped it out for Claude. Not the latest one, but the one previous. So there are some exceptions to that. DeepSeek R1 is actually pretty nice. So anyway, so we generate questions, we generate topics, or we got a bunch of topics, we're going to generate a bunch of articles, and this is our evaluation. Okay, and then here's our logic right here. So this is the loop. What we're seeing on the screen right now is that loop where I showed the diagram where the engineer is making changes or reading the output of the model, and then it's going to make change. It's going to judge and then make changes to the prompt, and it's going to go round and round until it gets it right. Well, this loop is basically that. This is that manual loop now done automatically, and just a quick overview of what's going on here. So we evaluate. Just kind of create a baseline. We evaluate where we're at. The evaluations, again, that's the loss. That's, you know, here's what's wrong with the data. Here's what's wrong with the output. Here's the score. And then we then go through and we run this in a cycle until we've hit our error goal. And what we've been doing is we're going to just get the worst 2 errors, because we could pass like all the errors in, but we found practically you can optimize this process by focusing on specific errors. Otherwise, the model starts to try to address too many things at once. Kind of like a human being, right? Like if we were to try to fix a coding problem and you were given a ton of errors, a ton of different problems. It's actually, what we're going to do naturally is we're going to focus on one at a time. So, and I'll talk more about that later because we're going to get into code generation as well in a bit. Let me check on time. Okay, I'm going to go a little faster now. Okay, so we adjust the prompt for errors, right? We collect all of our errors. We adjust the prompt for errors. We take our adjustment. We evaluate our adjustment to see how we've done so far. And then we do it again. And we just do this around and around until we get our final result. And I'll show you the output of that now. Okay. So this is that program that you see there running. Unfortunately, I'm not able to really show everything on the screen, but I'm going to try to show you at least what the final result here. And so what we're seeing here on the left is okay, so it's adjusting for errors. I made several key changes to address the identified errors. I've added stronger language about not filling in gaps with general knowledge, which addresses errors. I've added a guideline to explicitly state when a person or event or a concept mentioned is not in the article. It's just doing all the stuff that we would have done manually. It's actually doing it. It's doing it automatically with the model. And it's going to keep trying. And it's going to try a lot faster than we can. So we might be able to get to the heart of, well, there is no heart of the problem. It's just this massive LLM. So we might get to what we think is a working system faster than this system can, as far as, or with less iterations, but not faster. Because we can just run this, go have a coffee, and come back, and it'll be done. So finally, we end up getting to 90%. Let me just kind of, this is not helping you guys read this, I know. I'm sorry. I'm just trying to see it on my side here. Okay, and then we have our final result, and it's kind of hard to see, but unfortunately, everything is sort of squished. But it's basically created a new prompt, and it's created a bunch of requirements for that prompt below it. Oh, hold on. Just another run. Here, let's go ahead and run through the whole thing. And you can see some of the things that it's doing. It's giving guidelines, important guidelines, include this information. And if you've ever worked with large language models and actually tried to make things for production, everyone who starts out starts kind of doing this stuff by hand. And in this case, we're able to just sort of generate this on the fly. And this is a very rudimentary example. There are better systems for doing this, which we'll talk about in a second. But I wanted to just show how you'd be able to do this from scratch. Okay, and finally, we get to over 90%. So we started out pretty weak. I think it was, in the beginning, it was closer to 60%. And now using Quinn, using dynamic prompt generation or automatic prompt generation, right, we're able to get Quinn to behave, in general, for this particular task at over 90%. So let's switch gears back to the presentation here. So the traditional problem-solving process has been you pass a problem to a human being evaluates the problem, the human creates a solution to the problem, the solution is tested, sometimes automatic, sometimes the human just tests it, the outputs are produced, the human evaluates the output, and it processes the updates, just like we saw before, but now this is more generalized to any kind of problem, not just a prompt. Because the process that we just talked about, that we just went through, actually applies to many classes of problems. And in theory, I mean, most problems in general can be solved using this process.
10 minutes.
Thank you. So some people have probably heard intelligence is the log of compute. This is like a new concept intelligence is the log of compute. So if you pour compute in, you get intelligence out. And in the past, humans have had a monopoly on intelligence, and now for the first time, we're able to get intelligence out of a machine. And I think this is a pretty important moment. Now, of course, when did things get so flat that it doesn't really matter anymore, and we really still need the humans, and we still do actually. But generally, this is the way we are starting to solve problems with many of the projects that we're doing. We're looking at a way to create self-improving systems, and that doesn't stop at prompt engineering. It also is for coding, and we're also looking at how can a product team actually self-improve as well, or a product in general self-improve using automatic user feedback and doing the exact same process with code generation, configuration management, or configuration updates, and so on. So is this really intelligence? I think there have been a lot of statements, especially naysayers. This isn't really intelligence. It's just predicting the next token. It's not trained like a human being. It's not really intelligence. For all intents and purposes, we're extracting intelligence. It's clear to us because think about code. Code is a manifestation of intelligence, and we can actually generate code, and code that works well, and in some cases, code that is more thorough than the code that we would write. So we are working on an open source project right now that we are going to release at the end of SCaLE called the Automatron Use Solver project. And really what Use Solver is all about is being able to do all the stuff that we just showed, or I tried to show, unfortunately, sorry, in that manual implementation of prompt generation, but actually kind of build in all the tricks and do this in a way that's very easy for a developer, a Python developer, and eventually other languages can bring in. And so I'm going to show that now. I won't have time to do a full coding demo where I'm going to code it because, as we can see, there are some issues with that. But I will show you some examples of things we've solved just recently. And so what is USolver for? Prompt engineering, prompt generation, automated QA testing, data lake, data warehouse systems, generating SQL, generating an entire data lake pipeline. All of these kinds of, that world of things is actually that world, the data warehouse, data lake, is actually a really convenient world for tools like this we found. Web scraping and data extraction, data transformations, and inference cost optimization. So if I want to use a smaller model that costs less to do a very specific job, it's not going to do everything, but it's going to do one thing for me. I could use Solver to do this. I'm going to show you here. I'm going to show briefly, I'm going to show briefly the screen for the solver. So one of the things we wanted to do for the talk was build a scraper that could scrape all of the talks on SCaLE, on the SCaLE website, and also could scrape all the speakers that are on that are at the conference. And so anyone could do this. Anyone here probably can pop up Beautiful Soup and hack away at this, but we didn't want to write it. We started our code like this. The USolver decorator is pulled out from this, and I can show you what it. But when we show it this way, we don't show the decorator actually in the solutions. The way the decorator works is at runtime, if there is a solution, it takes the best solution that's available for that particular function at runtime, and it swaps it into the code, into the runtime environment. And when you're calling it, you're actually, so if I call parse conference speaker, I'm going to call the code-generated version of it that was generated by our solution pipeline. So we start out, and it does nothing good. This is what I wrote. I wrote parse speaker HTML and return a speaker object. That's all I told it. And I gave it a schema. That was another important thing. I gave it a schema, and we could review that. If anyone wants to review it with me afterwards, I'll be happy to show you. And then it starts working on it. And as it's working on it, it's telling you what it's doing. So in this epic, it implemented the function. And when it implemented the function, it was able to, okay, it got lucky. And usually this doesn't work out this well. I think the SCaLE website's really easy to parse. That's why it happened. But it was able to get 99.1% immediately. But there were problems. So let's look at what it generated. And if you're looking at this code, like, I didn't create a framework for scraping. I just said solve this problem, and I gave it a schema. And if you're looking at this code, 3 years ago, if I told you, hey, I got this code, I have this code, could you take a look at it? Would you have guessed that a human, or that a machine wrote the code? Probably not. And so for those who say this isn't intelligence, I mean, come on, like, it's pretty clear. I put compute in, and I got like what clearly looked like intelligence out, or a result of intelligence out. And it keeps going. Okay, it's been updated to handle test cases. It would be nice to probably have a diff here, but basically it talks about what it's doing. It's been updated to handle test cases where the company field is empty and so on. And as it's going, it's also documenting the newly discovered requirements. Because a lot of times, as you know, as engineers, you get requirements, and those requirements are not always clear. Well, this system actually it's discovering the requirements by looking at what requirements are sort of implicit based on the problems that it's finding as it goes, and it documents that. And it turns out that this is actually a very good way to solve problems, and so that's kind of part of some of the tricks that we've added to this. And then finally, it gets to 100%. And we also parsed all the presentations, and we did the exact same thing. So back to the talk. Okay, I think we're just about wrapped up now. So where do we go from here? I would say a lot of people are saying, well, is this going to be the end of software engineering as we know it? Are the large language models coming for our jobs? Yes and no. I think that this is really about, one, we shouldn't abandon what we know. We should try to build reliable systems. I think that we should shift from building components and move into building systems that are self-improving. We have to be the ones who build those kinds of things, and not just sort of build the one-off interface or the one-off script. Let the models do that. That's what they do best. And we should be building the systems that self-improve so that organizations can get a leg up by creating an engine, a product engine, instead of a product team that only turns when there's manual intervention. The heart of all this, the way you make this work, is verification. So if you have a way to verify your problem, you're almost there. All you need is input data. And in a system like this, you'll basically be able to solve your problem automatically. So whenever if you're struggling with, like, how would I use this for my problem? Just think, how do I verify my solution? And how do I get data? Synthetic data or actual data is okay. And I think in general, have to take a more machine learning mindset to everything that we do. Now, one would say, well, but you need less engineers to do a lot of the work that's being done because of large language models. I think what's going to happen is people are going to realize that they can build things very easily now. And so because of that, the expectation is going to be, well, build everything. Solve every problem. Every single thing that you see as a problem, I think the expectation is going to be, well, just solve it. There's very little risk. You might as well just build something for it. Why not? Even if a few people use it, so what? Just build it. And I think this is going to happen more and more until the point where everyone feels comfortable with the idea that they can create software. But what that means is real engineers are going to be needed in order to build these kinds of systems, and also to repair those problems when people just throw, vibe coding and talk to a large language model and have it like generate crap. Anyway, that's it. Thank you. I know I went over. Were there any questions? I could take a couple questions.
Thank you. The evaluator in the demonstration, you talked about that not only does it need to be able to call tools, but you need to give it a schema.
Yes.
That's a schema of basically how you want the result to be structured?
Yes, basically. A JSON schema, ideally.
Okay.
Yep.
Thank you.
In one of your slides on that text grad paper from Stanford, you showed the gradient descent and the backward propagation.
Yes.
The reason why recurrent neural work and LSTM failed or didn't do well is because of the vanishing gradient descent problem. And that's what the Google solved with the attention is all you need at paper with the solving KV problem. So did that, I didn't read that paper, did that paper going back and looking at the backward propagation?
No, are you saying, so let me make sure I understand. You're saying that the attention is all you need paper addresses the vanishing gradient problem.
Yes.
And you're saying, is there an analogous problem in the text grad context, and how would that be solved?
No, no.
Oh.
Did they go back and look at the gradient descent?
Did who go back?
Yeah, this text grad paper.
Did they go back and look at the vanishing gradient problem?
Yeah.
No, I don't think that applied in this case.
Okay.
So it's interesting thing about the text grad concept. It is not a strict mapping onto a traditional gradient descent. It's more of a high level sort of pattern, if you will, that is very much borrowed from the concept of gradient descent and back propagation. So a lot of the issues are not sort of addressed in the same way. So if you actually, one of the things we found was, you know, in the beginning of the paper, it talks a lot about how this is the same thing as basically autograd, and you're basically doing gradient descent. But it's actually quite different. And when you actually start to dig in, you discover that there are lots of little tricks that only seem to apply to text gradients. And so that's actually why we decided to not, we were using TextGrad for a while, but we noticed that it's quite limited because there's a lot more flexibility in what you can do. And we decided to not use it and build something different because we found that this concept is actually much more generalizable to other types of problems, and we prefer to.
Okay. Thank you.
Thank you. Sorry.
It's awesome, very interesting.
I wish the screen was a little bit clearer.
Yeah.
I would have been able to show more things. But
Yeah, it's a resolution. I think it's just so bad.
I was getting kind of tripped up because I had
Yeah.
to change my own screen.
It supposedly says here that your whole screen's supposed to set up to that, but still, it's bad.
Yeah, it doesn't look good.
Yeah,
So.
it's still really bad. Sorry about that. There you go. You want this or you want a microphone?
I'll do a mic.
You want
Sorry, I'll set up the headset.
Okay.
Oh, do you mind if I do the headset?
Whatever you want.
Yeah, the headset.
Whatever you want. It should be fine by now.
And what?
It's already the volume of trivia already.
Oh, really?
Do a
Up. Oh, you can hear my voice. Now I have something to fiddle with. All right. Okay. I can practice my stand-up set. Yeah, can you read it? I don't. How far in should I zoom? More? That should be good. Hey, everybody in the back, can you see the code on the screen? Is that a little, yeah, got a thumbs up? Hey, it's Divya. Hi, Divya. A little, you want bigger? More? Enhance? I can CSI enhance. All right.
I'm going to be flashing these cards to you so I don't have to go over you, okay?
Okay. Perfect. I'll be looking for you. Okay. The anticipation.
The thing is that the system has been kind of weird with the sound and everything, so that's why they want to give you guys time so you.
Like half an hour between, yeah.
Some of the other people don't have it. The other brokers don't have it. They have one that right after the other. So I'm wondering how they're doing it. This is just some of them.
That sounds brutal.
Yeah,
And they're
it's
small talks
like-
too, so if you, even if, yeah, like they're half an hour talks sometimes.
Yeah, it's just like one right after the other. I don't know how they're doing it here.
The best they can.
We have a little bit of time in between.
Yeah,
so
15
that's
minutes is perfect. No, it's all good. In fact, it's good that we're starting on time. I have a couple examples to go through. I'm going to target like last 10 minutes for questions, so I think I should be good. Yeah. Plus, I have the sleepy lunch crowd. We'll see how involved they are.
Saturday, everybody gets here. Or something.
Yeah.
Is that for lunch?
It's about 12:30.
12:30. Yeah, you're right. I get lunch after you.
Yeah, we all get lunch after this. I feel like the teacher who keeps the class. What? Oh, yeah. We're running all the data scientists where I'm at. We all use like Linux machines. It's nice. We thought we were going to be able to use the because we have like 3080s in these machines, and we thought like, oh, we have Linux 3080s. We should be able to do some stuff locally. No, no. All the models are still too big to fit on our machines. Hey. We got some, yeah. Oh, don't sit him over there? No, Isaac, you can't sit there. No, you're banned. I'm the speaker, I can say anything. Well, that's not true, but.
Okay, next we have Mr. James Healy with you. He will be presenting his talk, Harnessing Open Source Solutions in the Generative AI Landscape. Please hold your questions till the end.
Hey everybody. So harnessing open source solutions in the generative AI landscape. It's a very buzzy title. If you're wondering why it's so buzzy, I did have GPT write it. So, so this talk is going to be, well, before I start the talk, quick question to the room. How many people have tried to host their own LLMs on their own machines? Okay, so a little less than half, which is surprising, right? We're all software engineers, data scientists, but we rely on these proprietary companies to actually generate our output when we want to use generative LLMs. It's funny that it's come out that way. And so this talk is really about recalibrating what's possible and really conveying to all of you that yes, you can host your own LLMs and they're getting better every month, especially with every Chinese startup just pushing models that are nipping at the heels of Anthropic and OpenAI. So I want to step back and start my slideshow. Okay. So before we go into things, let's just have a brief timeline of the generative AI landscape. So in 2023, GPT 3.5 was released by OpenAI. And I think this is the moment the world really took note of how much promise there was in the generative AI space. We were able to provide prompts and get back pretty reasonable output. So everybody's mind was kind of blown. OpenAI dominated the scene. About 3 months later, a team from Berkeley released a VLLM. And VLLM is an inference server, also an inference engine. And what that means to us is it's a framework by which we can host LLMs. Pretty cool, but it's pretty quiet. And then 2024 rolls around, and every fun open source model is released. We have Llama 3.1, 3.2, we have Qwen 2 and 2.5, Anthropic open sources Mixtral, which is vision. It's a multimodal model, so you can have some vision aspects to your LLMs. And then, of course, December rolls around and DeepSeek releases DeepSeek v3, which blows everybody's mind. And just to add one more little, I have a lot of space on the screen, I can have one more bubble. 2024, we get Llama Factory, which was it was a library created by one individual. It's like the #1 trending repo sometimes on GitHub. Everybody loves this package, I do too. And Llama Factory is a nice Python package that lets you handle the training of LLMs in a disciplined fashion where you have a nice CLI, you set up your training within YAML files, everything's a little more robust. So, let's talk about VLLM. Let's talk about our approach real fast. Our general approach, and the approach I'm going to hammer home in this talk, is that we can fine-tune models with Llama Factory and use those fine-tuned models and host them ourselves with VLLM. And to go in specifically on VLLM. So VLLM is an inference server, like I sort of mentioned before, and the two big things that it introduced was this idea of page detention. If everybody's familiar with how LLMs work, a lot of it's based off of this notion of attention, where you give specific tokens within your generated tokens attention, but it's computationally expensive, and so what you end up doing is caching the attention for specific tokens, and that takes a lot of VRAM. So these folks at Berkeley figured out a way to partition their KV cache efficiently to reduce the amount of VRAM that was necessary. And they also have a pretty good implementation of continuous batching, which essentially means when you submit a request to an inference engine, when you submit a request to your model, and you submit another request like a second later, well, you can just append the latest invocation to your previous batch and cut down on your idle GPU. And the inference speed gains you get are pretty substantial relative to like Hugging Face or text generation inference, which I think Hugging Face is sort of inference server. You get 24 times speed up in like output tokens, so pretty substantial. And some things to consider with VLLM, you still have to host these models on your own compute. And when I say compute, I do mean GPUs or TPUs or inferential chips, depending on what sort of hardware you're going to use. And something to keep in mind is the bigger the model, the more parameters the model has, the more VRAM you're going to require. And so this is a pretty nice formula just for figuring out how much VRAM you need. Take the number of parameters that your model has, take the data type precision divided by 8 and multiply it by 1.2. But the way to think about this in your brain, if you have a model that has like float 16, take the number of parameters that you have, multiply it by 2. That's how many bytes you're going to end up using. So like a 7 billion parameter model, 16 float, you're going to need about 16 gigs of RAM to host that. Okay, and let's talk about Llama Factory real fast. So Llama Factory provides us with some streamlined fine-tuning, and they support a ton of different models, some open source models, such as like Qwen 2.5, all the R1 distilled models that DeepSeek put out there, Meta's Llama 3 models, Microsoft's V4 models. And the really cool thing about Llama Factory, it supports a couple different sorts of fine-tuning. So you can do some supervised fine-tuning, and you can also do some reinforcement learning with human feedback. By training models via PPO, you can train your own reward models, pretty neat. They also provide you the means to train models with more efficient methods like low-rank adaptation, LoRa. LoRa is pretty cool so far as cutting down the amount of time you need to train a model. So pretty cool. They also have some very good CLI and YAML configurations. And some more engineering considerations for Llama Factory. So I'll just drop this table real fast, and the sort of models that we're going to train today, and we're not going to train a lot of models because it does take time to train a model, and I only have you for about an hour. So a lot of these models are pre-trained. But if you want to train a 7 billion parameter model, you're going to need about 16 gigs of VRAM. Is that teeny? Okay. And before we launch into sort of our demo, I just want to make it clear when you might want to consider hosting your own model or just using a proprietary model. So what are some things you gain by hosting your own model? Well, you can cut down on latency. You know, you have to call a third party. The third party has to give your answer back. There's inherent latency involved. If you host on your own resources in your own cloud, you can cut down on latency if you have really strict SLAs. You also only pay for your hardware. So if you want to make 5 billion requests to OpenAI, it's going to cost money. If you want to make 5 billion requests to your own model on your own machine, you're only paying for the compute. So if you have a GPU for 2 hours, let's say you're paying $5 an hour for that GPU, $10. So something to consider. Another cool thing about hosting your own model, you can tailor the size of the model to your task. So let's say you have a model and you want it to turn the human language into SQL. Maybe you only need a 7 billion parameter model to do that. I think GPT-4o is thought to be a mixture of expert model. No one really knows the size of that model, but it's probably huge. It's going to take longer to get your response from something like GPT-4, which is a bigger model, than a smaller model with, say, 7 billion parameters. There's just less computations. You also reduce your dependency on black box third-party APIs. So I don't know if anybody else has experienced this before, but sometimes you use a model from a third party. It's just behaving differently one day. You don't know why. They don't really tell you what's going on with the weights behind the model. You just know something's up. It's weird today. It doesn't feel great when you're an engineer and you have an application. So if you host your own model, you have a frozen snapshot of weights at a given time, you can kind of rely on that a little more. And you also get some more fine-tuning options with something like Llama Factory than you would with a third party, which typically only supports supervised fine-tuning. You do have the option of trying out some reinforcement learning with human feedback on your own. You can continue to pre-train the model, giving it your own corpus of documents if you have a very specific use case. But there's some other things just to consider. You know, if you use a proprietary model, you don't have to host anything. They take care of all the hosting for you. There's inherent overhead you incur when you try to host your own stuff. Like, that will require a person. You also only pay as you go. So if you're only going to make 10 requests, if you only need 10 invocations from a model, maybe you shouldn't host your own model. You don't really need to pay for a machine. Also, let's be real, all these proprietary models are still beating out open source models. I wish that weren't the case because open sourcing is fun, and this is the OpenAI track, or the open data track, but these models are still beating out open source models. And of course, you know, 2 days ago, Quen released QWQ, which is a pretty big deal, but for the most part, proprietary models still have a bit of a competitive edge over open source models. So the TLDR, open source frameworks like VLLM and Llama Factory can be cost effective. They can help you customize your own solutions for your own production needs. They have some pretty seamless integration with one another so far as fine-tuning and deploying in production. And we'll get to a live demo in a second. But before I go to that live demo, since I have all y'all, I work for Crexy. We have a job opening for a data engineer to help us figure out how to label data at scale. And note what I did there. I used the SCaLE logo. I thought it was very clever. You guys had to chuckle at that. All right. So let's go into some notebooks. And can everybody see this all right? Okay, getting some nods. So we're going to skip the installation of Llama Factory and VLLM. We are using 2 Python packages today. This is a Python-oriented demo. And the reason I'm skipping those 2 installations was I only have you for an hour, and I don't want to waste that hour setting up machines. So let's go into Llama Factory. I think there's really 3 core aspects of Llama Factory. One core aspect is the CLI. Through the CLI, you can train your own models. You can merge different LoRa weights. There's also this aspect of setting up your own experiment via a YAML file. If anybody has ever run an experiment with a machine learning model in a Python notebook, you know how unwieldy those notebooks can get. And so having all of your training requirements in one YAML file is a godsend. And lastly, it's your ability to define data sets, point to those data sets, and train on those data sets is pretty nice. So let's take a look at what one of our fine-tuning YAMLs looks like. So here, I wanted to fine-tune a Quen 2.5 vision model. This has 7 billion parameters, and it's an instructor model. I want to train this using low-rank adaptation. I'm pointing it to a data set that I actually created for this talk called receipt VQA. The whole idea with receipt VQA is I have a data set. It consists of images of receipts, and I want to train a model about how to answer questions I have about the receipt. And you might be thinking, why are you training a receipt model? This isn't 2018. And the answer is because the data set was available on Kaggle. So I can also specify where I'm saving that model to. I can set up some training hyperparameters here. You know, what's my learning rate? How many epochs am I going to train for? I can set up some evaluation related setup, like how much of my data set I want to use strictly for evaluation. And if I take a step back, I can kick off some fine tuning just by executing this CLI statement right here. So I hit execute, and I hope for the love of God this works. It's a live demo, so you never know. So while this is training, or while this is setting up, I can quickly show, oh, it's actually training pretty fast. I don't have to do that much tap dancing for y'all. Okay, so this is actually training our model right now. Now note, I'm only training on 5 samples because time constraints, but I went through about 2 days ago and I trained a model on a much larger data set. And what we're going to see here after this trains, we're going to go to our outputs. So I am training this model here, SFT, but fast. And there's actually a lot of really nice output. There's a lot of nice things that we get for free by using this method. We get this nice README file. It displays what our hyperparameters were if we, say, wanted to give this output to a colleague. It has some checkpoints. Typically, we can also get some evaluation metrics. Let's look at an older run in which I did get evaluation metrics. I got this evaluation metric for a model I trained for free, along with some nice README information. That included training loss, validation loss, the point at the epoch where we incurred that logging. So we have trained a model, and you might think, okay, well, now what? What do you do now? What we can do is take the model we just trained and actually host it. So let me refresh this notebook. Okay, let me take this notebook here, and I'm now gonna throw what we just trained into the Python package called VLLM. So VLLM is going to be able to take the base Quen model that I trained on, and it's also gonna accept the model, the LoRa module I just trained, and hook it up with the base model that I specify. And we're going to host this own model. And we are then going to throw some receipts at it to see how well it did. So what we're seeing right now are some what we're actually doing is we're setting up a server to host our own model. What we're seeing right now are some server logs. A lot of logs that get spit out when you set up a server. It's like any other server. And you might think, you're getting a lot of warnings. What's going on with that? So we trained a LoRa model on a we trained a LoRa adapter on a vision model. Vision models typically have a vision backbone along with some LLM on top of it. And though we trained LoRa adapters for the vision component and the text component, VLLM does not know what to do with the vision LoRa adapter layers. So it's just a limitation on the VLLM side. If you train a vision model, you're not necessarily going to get the LoRa adapters that you trained for the actual vision part. And it's saying, hey, I can't find your model you're specifying. So let's see what's going on there. And I already see the error. Like many things, it's user error. So if I take a look at my directory, I have this folder called saves where I actually save my model. And when I try to host my own model, right now, hold on, there's a little bit of a lag between my CLI, here we go, between my CLI statements and what's actually appearing on the screen. We pointed to the wrong directory. So I'm going to fix that. Okay, let's host this. And while this is getting set up in my other screen, we're going to take a look at the receipt I am going to analyze. So this is the target receipt. Zooming in does not do anything. But let's see what this person bought. They bought some Pillsbury stuff, Starbucks. They bought soup. Who doesn't like soup, right? So let's see if we can analyze this receipt once my model is nice and hosted. It hasn't barfed yet, so that's always a good sign as you're programming. Right now, it's turning my model into a coup de graph. All right, my server's up and running. So I'm actually hosting this own model locally now. So another cool aspect of VLLM, you can actually use the OpenAI client to refer to your own model that you're hosting locally. So if anybody here is using OpenAI and you have your own source code to help you head up OpenAI, like I'm sure we all do, you can actually set up your own endpoint and you can simply swap out the model that you're referencing in your OpenAI client to your own hosted endpoint. It'll just work. So that's what we're going to do here. So I'm setting up an OpenAI client, and I'm going to point to a local host, and when I do so, I'm essentially able to hit up two models on my endpoint. One is the base model. The other is the lore adapter that we fine-tuned. So just note here that my vanilla model, I'm calling that the base model. The SFT model is the model I went and I fine-tuned. So round one, let's use the fine-tuned model that was trained. And what do I want to do? I want to take the receipt that I showed and I want to return all line items on the receipt, and I don't want it to hallucinate. Please don't hallucinate. For the love of God, don't hallucinate. So let's do that. It's saying, blah, model's not defined. And that's true because this is called SFT model. Okay, so if we go back to our terminal, we're able to see that the locally hosted model received some input, and it's done. And you're able to see the average prompt throughput was 271 tokens per second. Pretty good inference speed. So let's go back. This was my returned answer from the fine-tuned model that we hosted. So it's saying we bought some morphin meat. Yum. We bought some soup. That's correct. We bought some fruit and some Pillsbury stuff. That's all correct. So what we essentially did was we fine-tuned a vision model per our task. Pretty neat. We can also obviously swap out the prompt, return all line items. Shoot, I just want to know what was the store? The store I got this receipt from. Should be able to do that too. No, it's not. And that's because it's expecting some JSON. So just for the sake of this demo, I'm going to print the result. And the result was Memphis East 901.261.5079. We know that's not correct because we trained on a, well, essentially we were trying to predict on a receipt that was for target, right? So, shoot, our own fine-tuned model isn't that great. And let's think about why that is. We've all heard the phrase garbage in, garbage out. This data set has a lot of noise. So let's just try to use our base model. And one of the cool aspects about VLM, we kind of heard the past presenter talk about schemas. If anybody's used OpenAI, if anybody's used the outlines library, there's this idea about structured outputs where you can provide your own pydantic model. And if you have your own pydantic model along with a prompt, you can get structured output per your schema specification. And so for this example here, I defined a pydantic schema called line item. That's essentially, if we think about a receipt's going to have an item key. That was kind of the barcode for the thing you bought. It's going to have a name. You bought something. We're going to have a quantity associated with the item that we purchased, and that is going to have some monetary value. So that's a line item, and we think about it, a receipt is a collection of line items. So here I have a pydantic class called line items, and essentially I'm saying, hey, I have a list of line items, and this is what I want you to extract. This is what my schema looks like, and so let's hit up our vanilla model, and let's provide it our JSON schema. Bam. And it's saying, there's no line item schema defined, and it's because I didn't execute those cells. So let's try again. Okay, so this is currently producing some output. We can look back at our server logs here. The average prompt throughput blows my mind. 621 tokens per second. We got output. Let's look at our output. Some nice structured output from our model. We have item keys, we have item names, item quantities, item values. So everything we're expecting to produce, we got from our model simply using our pydantic schema and our OpenAI client. So pretty neat. And let's take a look at another use case we could potentially use VLLM for. Show of hands, who's heard about reinforcement learning with human feedback? Okay, decent amount of hands. Essentially, reinforcement learning with human feedback, and I'm sorry for everybody who already knows, I'm going to regurgitate what you probably know. It's a means by which you can train a model to judge the response of another model's output, provide a loss. You know, we heard the last speaker talk about this cycle, and then using that loss, you train another model. So basically, you have a critic model that's been trained on human preference, and this critic model is gauging the output of another model, and the error that the critic model perceives is backpropagated through the model you're trying to essentially train. And I have found a nice little diagram about reinforcement learning on the interwebs. The whole idea is that, one, you train your reward model to think or to sort of judge like a human, and then you're essentially taking an active model, which is this little red box. You are sending some query through that LLM, it's producing a response, and then you're using your reward model to criticize the output and use that criticism to make it better. So OpenAI used reinforcement learning with human feedback to train their GPT-4o model. Not really sure if they used it to train O1 or O3. It's a little bit of a, I don't know if anybody really knows. Somebody probably knows, I don't. So the two things that we need to do are train our own reward model and then use that reward model to train an active model. And you can actually do all that with Llama Factory. So let's go into those YAMLs that I mentioned. So the first thing we would have to do is train a reward model. You're probably wondering why I'm using Qwen 2.57b instruct instead of a vision model. It's because when I tried to set up this demo 2 days ago, I hit a bug that the entire world's hitting with Llama Factory. You cannot you cannot train models via PPO that are vision-based with Llama Factory. They suggest to use another repo, so we're going to stick to a purely text model. Anyways, let's look at this YAML file to train a reward model. All we need to do to train this reward model is change our training objective. Instead of doing supervised fine-tuning, we're going to say, hey, we're doing rewards model. RM stands for rewards model. And we're also able to fine-tune that via LoRa. I used one of the data sets that that Llama Factory provides by default called DPO English Demo. This DPO data set is essentially a data set that contains rejected and accepted answers. You can use that to essentially train a model on human preference. You train it to prefer the answer that was accepted rather than the answer that was rejected. And so after we train this reward model, we can then go in to our other YAML file called RLHF-PPO. And all we have to do to train a model that's being critiqued by another model is change the stage to PPO, proximal policy optimization. And we also point it to our reward model. That's our critic model. And so once you have these two YAML files set up, you can essentially do reinforcement learning yourself, or reinforcement learning with human feedback yourself. There's no barrier, there's no reason why only proprietary companies can do reinforcement learning with human feedback. And this model here that was trained with our critic was saved to our text reward model output directory within our saves folder. We can see it right here. And we have some training loss. It got better over time. I could have trained it for longer. It would have gotten better, but I didn't want to. So we now have a model that we can host locally, similar to how we did with our supervised fine-tuning model. So I'm going to go ahead and do that. Go back to the terminal. I'm going to kill the server I have going. It is no more. I'm also going to change my conda environment. Activate. It's a miracle. It's a miracle that I was able to execute that without a typo. All right, so we are now hosting our own model based off of the proximal policy optimization YAML file. So this will go ahead and get booted up. We're going to see a lot of server logs that we saw before. So far as setting up. These are all good because the model hasn't barfed yet. If it doesn't barf, you're able to run it. And while this is booting up, just for fun, I'm wondering how much VRAM we're taking up. So we're taking about 16 gigs of VRAM, and it looks like we're only using one device. We can change that the next time we run a model. One of the nice things that VLLM handles is multi-GPU distribution. So if you have a model, let's say it's like 70 billion parameters, you can't fit that on a single GPU. You can just get 4 GPUs and host the model on those 4 GPUs, and it'll shard the weights and handle that all for you. If anybody's had to do that themselves, I'm sure you know how big of a headache it used to be. You'd have to set up like DeepSpeed or another framework that was really tricky to get going, but no longer. You don't have to do that. It barfed again because I had the incorrect location for the saves directory. So that'll boot up. Okay. Okay, so this is booting up. Let's take a look at what this notebook does. The first round, I'm going to want it to write a haiku about sloths. I think sloths are cute. And I can also use the vanilla model. Can you write me a haiku about sloths? Guess what? It can. We don't have to wait for this model to boot up because it's going to give you the answers that I just showed you. So let's move on to the next example because I only have you for so much time. So we talked about 2 applications so far, both related to Llama Factory plus VLLM. Let's take a look at reasoning. So reasoning is it's the new kid on the block. Everybody's really hyped about these new reasoning models. O1 and O1 Mini were the first reasoning models on the scene. And the cool thing about reasoning models is how it gets to the answer. So what you're not seeing when you use OpenAI's O1 or O3 model is the reasoning chain. You know, its answers are really robust, and it's doing a lot of text generation behind the scenes and then synthesizing its answer and showing you that output. And it'd be really cool if we could actually see what that reasoning chain was. Because if you ask OpenAI to divulge its reasoning thought process, it's going to say, I can't do that, it's against my terms of policy. OpenAI doesn't want you to see. But we can use one of the open source reasoning models that either Quen or Alibaba has put out, and we can actually start to see what that reasoning chain looks like. So we are hosting our own model here. We're going to host the R1 Quen 14b model. This was a Quen 14b model that was trained on data that was generated by DeepSeek's R1 model. The idea behind that training process, I'm sure everybody's heard the term distillation recently. So you're essentially using some bigger, more powerful model to provide you curated data that you then train a smaller model on. It really wants to close. I'm not going to let it. So we are going to use this reasoning model. It's about 50% loaded. Something else to keep in mind if you want to host your own models, there is boot up time for your server, right? You have to provision a machine, you have to set up your server, all that takes time. If you're thinking about things like auto scaling, that is all overhead that you have to think about. So let me gauge on my other machine if this is still up and running. Okay, let me refresh this to see if that helps. Let's go back to our terminal. All right, cool. So our server is actually running. Let's look at what our reasoning model is doing. So I want to see if the reasoning model can figure out whether or not 9.8 is greater than 9.1. This is a quantitative exercise that I want the model to think through. I'm sure, I don't know if anybody's here has seen the strawberry example, you know, count the number of R's in strawberry. Machines can't do it. So let's see if our own reasoning model can figure out if 9.8 is greater than 9.1. And let's see how it came about to that conclusion. So we can take a look at our server. Oh, it's done. All right, so let's take a look at its reasoning. So it figured, hey, I can look at the whole number parts of both numbers. Both 9.1 and 9.8 have nines as a whole number, so let's go into like their 10th and 100th digit places. It then goes into some rationale behind whether or not 8 is a bigger number than 1. Guess what? It is. And it's able to arrive at the correct conclusion. 9.8 is greater than 9.1, which means 9.8 is greater than 9.11. So it did that right, and then after its reasoning context, it synthesizes its reasoning and provides the user with a little bit more of a concise answer. So, good job, machine. And let's take a look at the receipt. Let's take a look at this markdown of a receipt. If we note here, this receipt, I bought 1 asparagus for $1, I bought 2 broccoli for $2, and I bought 3 carrots for $3. I wanted to figure out what the per item cost basis is. Let's see if it can figure out whether or not a carrot is worth $1 and a broccoli is worth $1. So let's fire it off to the machine that we're hosting. You can see the server, it's handling the request, going through. And once we see that little OK here, we know that we've gotten an answer back. And look at that, we got an OK. OK, so sort of a longer reasoning chain here. So you can see it's really cool to look at this reasoning context. Let's just take a look at the asparagus. $1 divided by 1, that's $1. Done. Let's take a look at broccoli. $2 divided by 2 pieces is 1. So it's $1 per broccoli. It does so for asparagus too. So you see that it's able to do these quantitative assessments when I provide a prompt asking it to compare 2 quantitative properties. I don't know if properties was the right word there, but so it's able to do that pretty well. And then round 3, let's say I'm a lazy data analyst because once upon a time I was. And let's see if it can come up with an idea to analyze some data that I'm providing it. So I have this Pokemon data set locally, and I want to see if it can take a look at my Pokemon data set. It has a couple of columns. Those columns have certain data types. I'll also give it a sample of my data set. And I want to see if it can return Python code to actually think about an analysis that could run for me, because I don't want to think about it. You're thinking, hey, why don't you just use something like YData's pandas profiling? Won't that do a pretty good job? And the answer is yes, it'll do a great job, but I'm trying to demo you a reasoning model. So we're just going to go ahead and do that. So it's thinking about how it wants to tackle this analysis, and then it's going to provide me with some code I can run after the fact. Then take a look at this. This is a bit of a beefier, it's a definitely more involved ask that I'm asking the model to do. It has to think through how would I structure an analysis in Python, so it's going to take longer. The reasoning chain is going to be pretty lengthy. It's just based off of me running this prior to this demo. And it's done. Okay, so you can kind of think through, you can look through its reasoning content so far as what would be interesting to someone else if I were to do an analysis around this data. So, it's taking a look and it's noticing some columns or objects like ability and capture rates. It's also noticing that some of my columns are float 64. Maybe I can do something with those data types. And let's take a look at the final output. This is a little hard to read for me as well, so I'm going to zoom back in. But the first thing it would want to do is an analysis of type effectiveness. Then it wants to make a heat map of that type effectiveness. That's cool. Heat maps are always fun to look at. Then it wants to do an analysis of base stats. It looks like it wants to do some correlations between those base stats. Wants to do an analysis of the abilities, analysis of capture rates by generation, analysis of type 1 and type 2 effectiveness. So there's a lot to this analysis, and it kind of summarizes what it wants to do here. So it was able to sort of do a game plan for what analysis it wants to do, and more than that, it's giving you the reason why it decided that might be interesting. So if you're thinking about having your own models do some analysis for you and you want to QA its thought process, you can totally do so. I'm not going to go through and debug this code on the fly. I have about 19 minutes left. So leave that, what is that? What did our professor say? I'll leave it to the student, the reader. Yes, the exercise is left to the reader. Okay, last example. So we can also use VLLM to set up a RAG, a real-time augmented generation application. The whole idea here is you have some raw data sources. We are going to embed those, turn those into meaningful vectors, throw those into a vector database, right? And then, as a user, I'm going to ask questions against my vector database, and it's going to turn my question, also turn it into a vector, and it's going to do a dot product comparison between my user vector and the vectors I have in my data store. It's going to pull out answers, and then it's going to synthesize those answers and return a nice little response to me. It sounds like a lot, but it only took about 2 or 3 hours to code up, so it's actually not too hard to get going. And there's a lot of talks about RAG at this conference, and I think it's because they're fancy, they look fancy, and they're pretty easy to get going. So let's go ahead and host this model. I am going to nuke the server I have going out of orbit. Okay, so we are setting up our own Qwen 2.5 7B instruct model. We're going to host that locally. It does not like one of my arguments. It was yelling at me because I was trying to specify a lore adapter that I wasn't actually referencing. So, I mean, sorry, VLLM client, I won't do it again. So we are setting up our own server. And let's take a quick look at our code real fast. I'm also going to set up 2 other models, but just within the notebook for now. I'm going to set up an embedding model to turn vectors, or rather to turn text into vectors. And I'm also going to set up a re-ranking model. And the whole point of the re-ranking model is, okay, you retrieve some documents from your data store. Let's re-rank them to get a sense of which retrieved documents most closely match my query. And let's take that sort order in mind and only synthesize an answer based off of the top K many documents. So we're setting up those models locally. I'm doing that here. And let's take a look at our prompts. These are prompts that I did write, and the last speaker has me thinking that I should let machines write these prompts. So maybe I'll take a look at that in the future. But let's take a look at our embedding prompt. It's just saying, hey, you're given text data extracted from a Pokedex about Pokemon. The next user query is, hey, you're given Pokemon query. This query might include a request for details about the Pokemon data. And then finally, we have a RAG prompt, and that RAG prompt is essentially saying, hey, I had a user query, I retrieved documents, now synthesize an answer per my user query. Let's see if our servers are up and running. All right, so our Qwen model is hosted. Our other 2 models to re-rank and embed are getting set up as I speak. And we can take a look at our Pokemon data set. If I go into my Pokemon data, if I take a look at Pokedex CSV, it does not want to open because it has a really weird encoding type that I did encounter. I had to choose some funky ways to get around that. It has a really weird encoding. So we won't actually see what that data looks like, but that's fine. I don't have to tamp dance anymore because all my models are loaded. So first, I'm going to do a little bit of data pre-processing. Okay, I'm going to I'm essentially embedding my documents that I'm going to stick in a document store that we're going to host in memory. That is going now. And I'm also going to initialize an OpenAI client to my own synthesizer model. Note that this is also pointing to a locally hosted machine. Everything that I'm doing right now is local to this machine that I'm running on. And then I finally have some function called run query. And essentially what that's going to do is it's going to take the user query I'm going to provide it, it's going to embed it. It's then going to go through my document store and see which documents most closely match my user query. It's going to re-rank the results So I'm going to ask for 30 documents. I'm going to re-rank them. I'm going to choose the 10 best documents. I'm then going to throw those documents into my synthesizer model, and I'm going to have the synthesizer model actually produce the output that the user, us, that we're going to see. All right, so our in-memory model is created. Our OpenAI client is created. Let's run this query. So my own query, provide a breakdown of legendary Pokemon. Let's see. So it barfed. The model's maximum context length is 16,000. Okay, so essentially when I set up my VLLM server, I said, hey, restrict this to 16,000 tokens when you output answers. It's just not enough. So I'm going to bump that up to 32,000 tokens. So let's do that. So this is going to go through the process of setting up the server again. There might be a way to configure the server's configurations on the fly, now that I'm thinking about it. If you were to host this on your own production machine, you would be able to sort of mess with the configurations of that server. So it's something that I want to look into now that I'm thinking about it now, but you know, it's fast enough to set up. So for the purpose of this talk, I'm just going to nuke it and set it up again. So as that's getting set up, we can take a look at what that answer, pretty much, we can take a look at what was returned the last time I ran that prompt. And what it was able to do is say, hey, here's a breakdown of legendary Pokemon. I'll focus on the data points from the retrieved snippets. That was the retrieved documents from the data store that pertain to legendary Pokemon. And let's see what it returned. So it said like, oh, hey, here's some Pokemon called Dialga. That's pretty cool. Here's some Pokemon from the 3rd generation called Regice. Also, it found Mewtwo. As a Pokemon fan, I can say, yeah, this answer's pretty good, actually. All right, so my server's up and running again. Go back to my RAG application, my function that did not want to run. Let's try it again. All right, this time it's not barfing. Let's go back to our server. You can see it got a request. It's just churning through this. All right, it's done. And let's take a look at our response. And look at that. It's saying, hey, there's something called Dialga. There's another Pokemon called Lunala. We can change our own query too. Let's say, I don't know. Find me some cute Pokemons. Pokemon that are not scary. I only want cute Pokemon returned. It's going to go through. It's, again, turning this statement here into a vector that is getting, or that's being used to retrieve documents from my vector store. I have a response already. Look at that. It found some Pokemon. It found a Pokemon called Cutiefly. That sounds pretty cute. So it's pretty on the point. 10 minutes left. All right, that's perfect. I did a good job. So we have some output there. So, you know, RAG clearly working, pretty cool. And you might, you know, think, okay, cool. You've done like one invocation at a time. This is not going to handle production traffic. You know, I have like 30, let's say I have 5,000 users on my site at any given time. You're gonna have like a long queue. No one's gonna be able to get an answer back from your machine in a timely manner. But one of the cool things is that VLLM handles concurrency very well. I mentioned that innovation that they introduced called continuous batching, where essentially as more invocations to your engine are being received, it will append those to previous batches. And what that essentially means is it's meant to handle batching, it's meant to handle volume. And so I have 100 generated questions just about that I pretty much stole from the WikiQA data set. But it's open source, so I guess I'm allowed to steal from it. And what I'm going to do is take all of these requests, all of those queries, and I'm going to throw them against my model at the same exact time. I'm just going to throw those at the model in parallel. And we're just going to see here how well it handles concurrency. So it's doing all this in parallel. I'm not doing, my hands are off the machine. Look, I'm not even touching anything. It's just handling it. And we can take a look at the server logs. It's just churning through my requests. This is one GPU I'm using. So it's able to handle all of that input. It was able to answer 100 queries in 15 seconds. Pretty impressive. And if you were really worried about scale, obviously, you could obviously throw more GPUs at the problem, host in parallel, and that would just kind of speed things up. So I'm going to end the demo there. So we covered 5 use cases. We covered how to do supervised tuning and hosting your own model. We covered how to do some reinforcement learning with human feedback. We covered how to look at reasoning chains, reasoning models. We covered RAG, and we just talked about sort of more production-minded concurrency problems. So this is a pretty mature framework. I can tell you that we've been able to host some LLMs at Crexy on using VLLM. It's worked very well. So this is the use cases there. There's a lot of really big companies who are pouring money into this open source project, like Roblox. Go figure, they're like a really good tech company. And yeah, that's the talk. If anybody has questions, shoot away. Yes. Mm-hmm.
First, thank you for the talk. Very insightful. So my question is, I've heard a lot about Unsloth, which is becoming very popular. And my understanding is that it can work inside Llama Factory, but I'm not sure. I'd love to hear your thoughts on it.
So, and does anybody, so before I answer, does anybody else in the audience have experience with Unsloth? Okay, I was going to defer to somebody who knew. From my understanding, Unsloth is a framework that helps you quantize your models. And so quantized models are a big deal when you need to fit a really big model into your own memory and you start to play around with the data types. Unsloth has some pretty cool means by which you can really shrink this memory footprint of a model. So Llama Factory has bits and bytes support, which is pretty similar to Unsloth. I wouldn't be surprised if they have direct Unsloth. I wouldn't be surprised if they supported it, but I'm not entirely sure.
Thank you.
Anybody else? Any more questions?
Does Llama Factory, or I guess the vision models you've been showing, how does that handle if you wanted to work with more like structured data, like CSVs, things like that in the context of RAG?
Yes, so I showed the image example because that's a little more complicated than the CSV example. So what you can essentially do is set up your own data set, and if we actually take a look at our at the data set that we created for the Llama, for the VQA receipt example, here we go. This is the actual JSON that I trained on for that VQA example. And this looks like a JSON-L where essentially, if you've ever trained against OpenAI, we're using the shared GPT format where you have a role here that was like a user query, and we're saying, hey, assistant, I want you to return Safeway. And all you would have to do to get your own CSV thing going, just replace, this is a placeholder to refer to an image. So essentially what I'm saying here is, hey, given the image down here, name of the store, please, return Safeway. Just get rid of the image. You'll be able to train on your own data. You just have to make the JSON file. Pretty cool.
Just a quick question. How does Llama Factory integrate in with like ML Flow?
Great question. So if you think about Llama Factory as a CLI, you can run CLI statements from an experiment that you have set up in MLflow or in Metaflow or whatever experiment tracking framework you want to do. You could kick off a training cycle by figuring out how to execute your CLI statement within your Metaflow experiment.
Hi, this is kind of a bigger picture question. It seems like newer models that come out continue to be larger and have larger requirements for hosting them. So from like a personal perspective, if people want self-hosted models for privacy reasons and self-sovereignty reasons, it seems like it's getting harder to do this, not easier. And I'm just curious if you have any thoughts on whether you think this is going to get harder over time or get easier over time?
That's a great question. What we're seeing in the open source community is actually a trend towards smaller models. So if you, for example, if you take a look at the Qwen 2.5 models that came out, they're pretty robust. And those models vary anywhere from 1 billion parameters to 32 billion parameters. If we talk about our, sort of our trick to figuring out how much VRAM we need per number of parameters, if you're running on like a, I don't know, like on a 3090, how much VRAM does the 3090 have? How much? 24 gigs. So that would be able to host like a 7 billion parameter model pretty well. And we also talked about this idea of quantization. So you're able to cast your model's data types to a smaller format to take up less room in VRAM. So what that essentially means for you as someone who wants to host their own model on their own machine, you could take a 32 billion parameter model, quantize it to say int4. That means that you only need 0.5 bytes per parameter. And what that means is a 32 billion parameter model you can host with 16 gigs of VRAM. 32 billion parameter models are really good. The Qwen's QWQ model that they released 2 days ago, maybe 3 days ago, is 32 billion parameters. It's as good as OpenAI's O1 mini model. I mean, how good is it? How much better can it get? And they're going to keep on trending down, I think, so it should get better over time.
Anybody else? Questions? Okay, since there's no more questions, please round of applause for Mr. Healy.
Yeah. Let me share my LinkedIn. Yeah.
Okay, great. Good talk. Very, very good.
Thank you.
Very awesome.
Awesome job.
Thank you. Yeah, I should do that, shouldn't I? So I'll talk to the conference folks to see how I
They make everything available on YouTube.
Oh, will it? Like the notebooks themselves? Oh. Oh, yeah, I can host. I can. I want to get my hands on the code, when I see these presentations. So I'll definitely. I'll talk to the SCaLE folks about how to get like a GitHub link associated with the presentation. But you had a question.
Yeah, just
perfect.
LinkedIn.
I almost stole your microphone. It's in my back pocket still.
Well, I think we're going to need it for the next people.
No,
person.
I'm taking it. And my name's James, by the way.
Shonan.
Test.
Test, test. Test, test. Okay. Should I start or should I start? Hello, hello. Yeah. Hi everyone. So I guess it's 2:30 and then, we can slowly start. So hi everyone, I'm Nitish and today I'm going to talk about like how you can measure the effectiveness of your RAG or Retrieval Augmented Generation applications. Yeah. So before I start, a bit about me. So my background is mostly in data or ML engineering. So I built data pipelines for a lot of big companies in like Europe. And currently I work as a developer advocate at Couchbase. And what we do, so for those of you who are not familiar with Couchbase, we are a data platform for AI applications. We have a document-based database, document store. We support like vector search, and like we have even started like adding AI services to the platform, so you can run large language models in the same network as your database. And as part of the developer experience and ecosystem, we built a lot of integrations with the developer community. For example, things like LangChain and like Llama Index. So we built out integrations for Couchbase with all those platforms. So I'm actually based in Munich, Germany. And yeah, so let's get started. So today we'll cover a bit about like what retrieval augmented generation is, and then we'll show like a couple of demos, and then we get into like how you can evaluate retrieval augmented generation based applications, how you can write like unit tests, and how you can use large language models as judges. Yeah. With that said, yeah, maybe let me just do a little show of hands. How many of you have tried out RAG? Okay, quite a bit. Yeah, as has been the trend last year, it's getting like more and more popular. Everyone, or like a lot of you have tried it out. And so today I'm going to see like how you can measure like the effectiveness of your RAG. So just a small motivation for using RAG. So LLMs are quite powerful, but not completely reliable. So for example, this is like something that I tried with ChatGPT. I asked it to perform vector search with the Couchbase SDK, and I got some code that looks quite right, but it's not completely right. And it's these problems that like really are really hard to debug. And yeah, I mean, so because I knew Couchbase and I know that this is not the right syntax, I asked ChatGPT, hey, this code snippet is incorrect. Can you generate the right code? And guess what? Yeah, I mean, ChatGPT now agrees to me that, okay, yeah, you are right. But it then says that Couchbase doesn't support vector search, which is also not right. I mean, the problem here is that ChatGPT didn't have like the knowledge cutoff, didn't know that we had like added vector search support at the time of its training cutoff. And so it basically comes up with like how you can use files for vector search and Couchbase for your documents. Yeah. So this is what we are trying to solve using RAG. So you try to avoid hallucination and improve the knowledge cutoff. Yeah. So this is like the popular architecture for the RAG. So you basically have some internal or like some data that the LLM might not have. As part of its training data, you put it into a vector store. And then whenever the user asks a question, you basically use that question to retrieve some relevant knowledge from the vector store, and then you pass it on to your large language model in its context so that the large language model can use this knowledge that was retrieved from your retrieval stage to generate the answer. Yeah, I mean, typically you would embed your documents so that you store the textual information in numerical form, which is easier to work with using like embedding models. Yeah, I mean, so essentially you have like two major steps. You have the retrieval step, which is concerned with getting your getting the knowledge to the LLM, and then you have the LLM, which basically puts all this information in a human readable or human understandable form. And yeah, I mean, let's start with a quick basic demo. Yeah, it's not this one. So this is like the classic chat with PDF application where you can upload like a PDF document and then ask questions about it. And let's just start with it. So here what I'm doing is we have this Python LangChain integration, which tells you how to use Couchbase as a vector store with LangChain. I've just exported this page as a PDF, and now I'll just upload this PDF. Yeah, not this one. Yeah. So I'll just upload it. So what is happening right now is like I'm taking this document and I'm chunking it into subsections, or like splitting this document into parts with some overlap between them, and then inserting this document into Couchbase along with the embeddings for those segments. And we can also see this on this Couchbase cluster I have here. Yeah, so you can see things like, so this is how like the document looks. So you have some information about, yes. Yep. To create the embeddings. Yeah, I mean, so in this case, I'm just using the OpenAI model. So I think it's, I mean, I can check that. Yeah, no worries. I believe it's the Tech ADA one. Yeah, it's the ADA, text ADA 2 model. Yeah, so essentially you have like the text, and then you have like a embedding, which is 1536 dimensional vector, and then you have some information about the document and like the source, the file from which it was extracted, and also the page number in this case. And we also have like an index here, which allows you to perform vector searches. So here you can see that, yeah, I'm doing basically dot product similarity for this and fetching the data. So with that said, let's just ask this question. How can I help you? So I want to use Couchbase as a vector store in LangChain. How can I do that? So now what is happening right now is like there are two responses that you will see. One is using the RAG and one is without the RAG. And if everything goes right, we should see the RAG response has the actual answer while the plain LLM answer wouldn't have that. It would, yeah. So this, the red logo one is the RAG application, and here you can see the steps like install the LangChain Couchbase package, set up the Couchbase credentials, connection object, bucket scope collection, and then it tells you how to use it. And if we wait a bit, we should see the response from the plain LLM as well. Yeah. So here it says, yeah, it's an open source library, and that you need to create an interface that allows LangChain to interact with Couchbase. So here you can clearly see how the RAG helped solve this problem of knowledge cutoff here. I mean, this implementation, it looks sketchy, but essentially now you get like an idea of what a RAG is. And I mean, I can also take a minute to show you like how simple the code is. So I'm using LangChain for this. So essentially you have like a vector store object, and if I go there, yeah, it's just basically initializing the Couchbase vector store with like the cluster object, which is essentially our connection using the SDK and information about the bucket scope and like the embedding model that you are using, and also the index name. And so you are also using this as a retriever, which is basically used to retrieve documents that are relevant to your query. And there's some caching involved so that you get faster responses if you have the same questions repeated. And yeah, so this whole chain is where the RAG is. So you have a context that is fetched from the retriever. I mean, the question is basically passed through it, and you have like the prompt, which is coming from here. And you have like the LLM, which is GPT-4 in this case with temperature 0, and then you are just parsing the output. And in the case of the LLM without RAG, you just have this, you don't have this vector store component. That's essentially how simple the code is. I mean, the rest of it is mostly the UI code. Yeah. And if you look at like the different components of a RAG, these are the main parts. So you have like one, which is the ingestion of documents, where you ingest the documents that you want the LLM to address that might not be part of its training corpus, for example. Or it could also be your private data that the LLM doesn't have access to. And then you would create like, you would embed this data to create those embedding vectors using those embedding models. And in the retrieval phase, you have a vector search, which you use to generate the relevant documents. And then you can also have a re-ranker. The goal of the re-ranker is to arrange these, or to rank these documents that are returned from the vector search in such a way that it works better for the LLM. Mostly the LLM tends to ignore the results in the middle, so it focuses on the results that are at the top or at the bottom. So the re-ranker tries to address this for you. And in the generation of the answers, you use the ranked documents as context, and the LLM would basically generate a coherent answer based on that. with that said, like I would also like to go into a bit more complex demo. So this is basically the chatbot based on documentation. So if I go to like the application, so essentially what we have done is we have indexed the entire Couchbase documentation and split it into chunks and stored it in a Couchbase store or database. And now you can ask questions like what I did earlier. So I could ask things like, how can I use vector search with Couchbase? So this is what we tried to do initially with ChatGPT, and it failed. And yeah. So now this whole text is converted into embeddings, and then this embedding is used to retrieve documents from the vector store that are relevant to this, answer this query, and you got like you got an answer. So you have things like ensure that you have search service, which is doing the vector search in this case. And it also asks you to create a vector search index. And you got like a proper search request here. And you also have some references if you want to follow along with this. So if I open this, this should be the same code as what we saw earlier. Yeah. I mean, I can also ask follow-up questions like, so this code is in JavaScript. Let's say I want this in Python. Can you write the code in Python? And yeah, so now you can see that like the code generated is from the using Python instead of JavaScript. Yeah, I mean, if you, so the one thing which I want to show you here is like how this whole thing works. So what I have here is, yeah, let me just, so I can look at the stack trace or like observability for this run, and here you can see that like how can I use vector search with Couchbase, and you have the whole message history, and then you have like some component that summarizes this, and this is what is the summary of the conversation, which is Couchbase vector search Python example. And then you use that to retrieve documents from the vector store that meets the requirements, and essentially then you send this entire document content into this LLM, and the LLM generates the answer for you. Yes. Yes, this is Langsmith. But there are like many other alternatives, and almost all of them look similar to this one. Yeah. Yep. Yes. Sorry. Is it better or? Yeah. Yeah. I mean, I'll get to the importance of like using an observability platform in a bit, but this is essentially what you have here. And this is the whole workflow for this. So you have the ingestion step where I ingested the whole documentation website. I generated the embeddings for it and stored it in Couchbase. And then when the user asks a question, you generate like, you fetch the relevant documents from the vector store and then inject it into the prompt from the large language model. And then the LLM works with this context to generate the answer. Cool. So with that, now we'll get into a bit more about how you can use or how you can improve or like protect the RAG from hallucinating and doing weird things. So one of the methods that's really common in software engineering is unit testing. So you can do something similar to that in RAGs as well. For example, there could be cases like you don't want the response to be beyond certain length. So these kind of things, you can write simple, like small pieces of code in your application to check these things. And for example, there are things like code snippets, which are always quite tricky. So you can do, there are multiple options. So you can have like a sandbox environment where you can run those code snippets if you like, or you can also do parse the code snippets that are generated. There are also other things like leaking sensitive data. So for example, if you know that maybe the LLM could spit out some emails for some reason, you could have like a regex that validates that the output doesn't have any emails. And this is something that you can run in your CI like traditional software engineering with each change that you make to your RAG to ensure that you are not breaking the system. So that's like one of the initial steps that you can do. Following on, how about measuring the quality of responses? Before we get there, the main challenge with LLMs are non-deterministic. And with traditional NLP metrics, most of them, they work with like string matching and those kind of things, or like n-grams and like longest substring and things like that. But in this case, for example, you have a question and 2 answers. What are the advantages of using Couchbase for high performance applications? And the 2 answers are quite similar. So one is like Couchbase is designed for high performance applications due to its distributed architecture, which ensures scalability and fault tolerance. Its memory first approach speeds up data access while the built-in caching layer minimizes latency. Additionally, Couchbase supports ACID transactions, making it reliable for mission-critical tasks. And the next one is like Couchbase offers excellent performance for demanding applications by leveraging its memory-centric architecture and automatic sharding. The integrated caching mechanism reduces response time significantly. Furthermore, its ability to handle concurrent operations efficiently ensures that high traffic clouds don't impact performance. So if you look at these 2 answers, they are quite similar. But if you use any of the traditional NLP metrics, they don't perform well. You won't get the same similarity. You could use things like cosine similarity or any of those similarity metrics if you like by converting this into embeddings. That's a possibility. And that's also something that we'll see in a bit. So, there are 2 main approaches that you can do. One is like use a human as a judge, where there's a human who is manually evaluating each output for whether it's good or bad. The good thing is it's really accurate, but it's also quite expensive and hard to scale. The other option is to use an LLM as a judge. Because LLMs are really good with text, that's something that you can use to make the LLM judge the answer that was generated. And typically, the process involves you would create a reference data set with some questions and ground truth answers. And then there are like some metrics that you can use, like context precision, faithfulness, semantic similarity, etc., to see how the answers generated by your application and the reference answer vary. One thing to remember is that like even your LLM that's acting as a judge could hallucinate, so you would need to have some kind of workbench to ensure that your LLM is not hallucinating again. So we get into the same problem. Yeah. And so how do you come up with like a reference data set for using the LLM as a judge? So you ideally want to have like diverse examples that cover all kinds of different use cases that the user might ask the application. There are some possibilities for you to generate it synthetically. I mean, it works okay. So if you, the idea is that you give some context to the LLM and then ask it to generate some questions. You could also use an LLM to come up with use cases to test. The other option is to use examples from users. So this is where if you have an observability platform, you could use the traces from it. Or let's say if you have like an existing forum or Stack Overflow, you could use that. So in our case, like for question and answers, you have a lot of questions already posted on our forums and Stack Overflow that we could use to generate like the reference data set. Sorry, yeah. So coming to how you would use this reference data set to come up with some metrics for judging how good your RAG is. So typically you would split this into both the metrics for retrieval stage and your generation stage. The idea is that your retrieval should always fetch the right documents for your LLM to work with. And in the generation step, you try to ensure that you have most of the documents that are part of the retrieval stage are part of the actual answer that you send to the end user. And the two common metrics for retrieval is like context precision and recall. And for generation is faithfulness and answer relevance. I'll get to that with an example shortly. So context precision, it refers to the proportion of contexts that were retrieved that are relevant to the ground truth answer. Whereas context recall comes to it from the point of the ground truth answer. So you come up with like some facts in the ground truth answer, and then you check if those facts are present in one of the retrieved contexts. Whereas with precision, you basically look from the context and the answer, whereas this one goes the other way around. So I'll just give an example. So here, sorry. I mean, here you have the same question. What are the advantages of using Couchbase for a high-performance application? And here you have an answer. This is the ground truth answer, which is like Couchbase is ideal for high-performance application because of its memory-first architecture and automatic sharding, which ensures scalability. Additionally, its built-in caching layer minimizes latency. And you also have this retrieve context that were retrieved from the vector store when you had this question. And it goes into things like Couchbase provides a memory-first architecture and automatic sharding, which enable high performance and scalability. So this is, if you look at it, this is relevant to the answer. And the next one is its built-in caching layer reduces latency by serving frequently requested data quickly. This is also relevant. Whereas the next one is Couchbase supports full-text search with FTS indexes for advanced querying capabilities. So if you look at the answer, this is not really relevant, while it might be useful. And if you look at the precision, now, so the precision, we look at the context, and here you have two contexts that are relevant to the answer. So you have something like 2 by 3, whereas the third one is irrelevant. Sorry. Yeah. So the precision is, so you have this retrieve context, right? So this is basically from your vector search result. And you are, I mean, this is basically fed to an LLM, and the LLM tries to come up with like the facts in the ground truth answer. And then it checks for these facts in all of these retrieve contexts. So in this case, it's like architecture, sharding, caching. And when it's, so here, if you look at like the first and second one, second retrieve context, it covers these two. Whereas the third one has nothing to do with the answer. So it's not really relevant. And that's why your precision, that's how the precision is calculated. I mean, these are coming from Ragas, which is like an open source library. Yeah. And recall is basically checking how much of the answers you have in your retrieved context. So in this case, all of the facts are part of the retrieved context. So your recall is 100%. And now we go to the evaluation metrics for generation. Here, the idea is that faithfulness. So with faithfulness, you try to ensure that your generated answer follows the retrieved context. Because ideally, you want a lot of weight to the retrieve context, because otherwise there's no point of this RAG. You could just as easily use the LLM directly. And there's another component which is called answer relevancy. What it does is it measures if the generated answer addresses the user's question. And how does it work? So essentially what's happening is you take the ground truth answer and generate questions based on the answer using an LLM. And you do like an average of the similarity of those generated questions with the question that the user asks to essentially come up with how relevant the answer is. So if the questions that were generated based on the answer were similar to the original question that the user asked, the answer is deemed to be relevant. Whereas if it's not, yeah, then maybe the LLM hallucinated or like answered something tangentially instead of directly answering the user. And with the same example, you can see that like the faithfulness is high because you have two relevant contexts that were part of the answer. And the answer relevancy is also high because it answers the original question that the user asked. And I mean, this is where it gets tricky. Like, so you need to have some kind of interpretation for these answers. So if the faithfulness is low, this means that your LLM is not using the context that was provided to it, or it is mostly relying on its inherent knowledge. This could mean that you might have to index relevant data, or maybe you need to create that data in the first place. And you could also have the other case like context precision low, which means that you have a lot of irrelevant contextual information. And yeah, I mean, this could mean that you might have to improve your retrieval mechanism, maybe add some filters to the documents that you are fetching. I mean, on the right, you have like an example of a metric for one row of the data. So it says like the context precision is 1, faithfulness is 1, answer relevance is 0.97, and the context recall is 1. So this is really high. But that's where it gets tricky. So now that you have like a single metric for your answers, you could even do some kind of averaging over the ground truth data set that you use for evaluation. But does it mean that your RAG is good? I mean, you can say that it's good, but there's always like some component that maybe it's not as good as human evaluation. And that's where it comes, like you have another step where you can use a powerful LLM, like one of those reasoning LLMs or chain of thought, process with some good prompt engineering to generate like a classification for the answer, like how good the answer is, and also some critique for the classification. So here, what you're trying to do is have some kind of, I mean, you can also go like a bit fancier with the classification, but it's easier to just start with something small, like, okay, maybe the answer is good or not. And also you want, it's really important that you have some reasoning for the classification. And yeah, you basically do this for the evaluations. And yeah, with this you can come up with like kind of like a single metric for how good your RAG system is performing. But remember that we already spoke about how user feedback is the best form of evaluating a RAG. And this is where, I mean, if we could somehow align the user feedback with what we have from the LLM, it would be really awesome. Because then we could use this aligned LLM as a judge, which would be a proxy for like the final system's performance. And one of the ways that you can do it is like using a domain expert, where, yeah. So now that we have each question, for every question you have a critique and classification from both the LLM and a domain expert, you could do some kind of analysis between how much they follow each other, and if they are off, how are they different. And this is what you do. So you basically, and this is where it's easier with like binary classification, because if you do like it's like, say, like a scoring scale from 0 to 5 or so, then it becomes a lot more difficult to manage this. And yeah, so essentially with this, you can see that like for each iteration, you can come up with like, okay, how good the model and the human judgment aligns. And the idea is that if they are not aligned, you try to see if there is something that you can fix in your application. You need to look at the logs to see why they differ and which one is relevant. And then you try to come up with like some classes of problems that your RAG application cannot answer properly, and then you try to see how you can address them. Yeah. And one thing to remember here is that, yeah, how do you train the LLM as judge to be better aligned to the human judge or like human domain expert? And this paper addresses that to a good extent. So it's from UC Berkeley, and who validates the validators. And this is a really good paper where they tell you some ideas that you can explore to ensure that your LLM as a judge and the human domain expert, they are getting more and more aligned. And one of the things that they mentioned there is to have some examples from the human domain expert that are provided as like a few short examples to the prompt that is provided to the LLM as judge to evaluate the overall performance of the RAG. Yeah, I mean, you could also go more fine-grained in the sense that you can have like similarity between the question and existing questions that have been annotated by the human domain expert and put those into the prompt so that like you have more close alignment between the LLM as judge and the human evaluator. Essentially, the idea is that if you have an LLM as judge that is quite aligned with what the human domain expert or the feedback from the human domain expert, you could use that as like a proxy for how good your RAG performs. And you also need to do a periodic review of this alignment, especially when you change some of those metrics or like some of those embedding models or like chunking strategy and those kind of things. To conclude, I would like to give some takeaways from it. So if there's nothing that you would take away from this talk, I want you to focus on this application logs. It's really important that you have some kind of application logging so that you know what are the kind of things that your users are trying to do with the system. And if possible, try to observe them as much as possible, especially when you start off, so that you can find some groups of questions that your application is serving well and some groups that might not be served well. Then it's always a good idea to add some sanity tests to validate outputs. Things like structured outputs are pretty good. And one of the things that you get with this application logs is it helps a lot in coming up with reference data set to tune your context precision and faithfulness so that you know that your retrieval system is working and then your generation is also following the context that is provided from the retrieve system. And then you can, once you have this system in place, you can come up with like a reasoning LLM or like a more powerful LLM to do an evaluation of the generated answer. And along with it, you have a domain experts evaluating these answers, and then you try to align the reasoning LLM to the domain expert. And you basically continue the same process throughout. Yeah, and I have some resources here. So we have a tutorial that tells you how to evaluate RAG responses using RAGAS. Yeah, you have all the metrics which are documented on RAGAS site as well. And there's also a good blog post from Hamel Hussain, which talks about using LLM as judges. And yeah, you also have all these demos that we saw earlier. So all of them are public, so you can use them if you like. Yeah, and yeah, I mean, that's all I have for you today. And if you want to reach out, you can always reach out. And yeah, and if you want to try out Couchbase, we have this forever free tier in Capella. So it's completely managed for you. You can go to this link and sign up. Yeah, and try it. And if you have some feedback, we are always open to them. And that's it. Yeah.
Nitish, can I ask a question?
Yeah.
Here.
Oh, okay, sorry.
Okay. I mean, if I take your entire RAG code, just replace that Couchbase vector DB with Chroma DB.
Yep.
Will keeping the inference model and embedding model, everything same. The answer will be the same?
I mean, you cannot say that the answer would be the same.
I mean, the probability,
Yeah.
forget about the probability.
Yeah.
The performance, everything will be the same, right?
Yeah, I mean, it depends on like what, basically the vector search algorithms that are used by ChromaDB versus Couchbase. But typically, you would have like similar answers with both.
Okay. Yeah, and another thing I noticed with the RAG is that when I give the PDF with the text document alone, it gives good answer. But when I have the same thing with in a rectangle, data inside the rectangle, like a organizational chart, it doesn't do very well. Did you
Yes.
notice that?
Yeah, so that's a really good point that you make. So that's because like you need, so most of the PDF parsers that are like coming out of the box, they are mostly work with text. For these, like you need to basically parse the entire document and try to identify like these shapes and stuff. So we actually have something on our cloud service that does that. It's called unstructured data service, I guess.
Okay.
Basically, it allows you to parse parts of the document, and like it can parse images and tables and those kind of things and tag it in a certain way so that you can get better results from your RAG.
Okay. Thank you.
But there are also other services out there that you can use for it.
Okay. Thank you. Thank you.
Any other questions?
Hi, sorry, oops. Sorry, not really a question, just an announcement. There's going to be a Birds of a Feather meetup at 6:30 p.m. around the corner for anybody interested in search, including vector search, full text search, and analytics. Thanks.
Okay. Anybody else?
So this is actually a comment for the gentleman. I think you were asking about doing RAG on some of the PDFs that have these texts that doesn't seem to come up properly, right, when you prompt it. Yeah, so the thing I've learned is with PDFs, it actually is very different than a regular document, right? Like a Word document or text document or Excel file. Because with PDF, there is a lot of, I guess, XY coordinates for everything that shows on the PDF, so that no matter what device you open up your PDF in, it always shows up at the right place. So because of that, like a lot of the text, like they're all not, I would say like they're not organized logically, right? And so I think some of the AI models, they have a huge problem extracting that. So that's why like a proper tool to parse everything would be relevant.
This PDF extractor comes before the AI model, right? We are using the PDF loader. That is feeding into the embedding model, right? So its problem, as you said, is coming there, not at the AI model. Yeah, yeah.
Yeah, so this is like, so what you do is like have some kind of OCR, so optical character recognition, so it works similar to those.
Okay.
I mean, there are like libraries out there,
Okay.
so I mean, most of it is taken care of.
Yeah. I mean, when you give a demo to somebody, you give the regular one, the URL one, it gives perfect answer.
Yeah.
So you give the PDF this one, it gives an embarrassing answer.
Yeah.
Yeah.
Anybody else? Okay, let's give a round of applause to our presenter. Thank you.
Now it's, oh, now I have to talk really quietly. I hate that. Okay, I'm warning people now. There's going to be a sweet spot, which is probably right about here, unless you're young. If you're young, you can probably sit in the back, because then the fonts will be, and the pictures will be visible. But if you sit really close to here, my voice usually gets like this, because I get really excited. So I'm just warning people, either you're my age and are hard of hearing, and so that's great that I start talking like this, or, okay. Yeah, exactly. This is the font for the whole thing. No, it's not. That's terrible. Hold on. I'm turning myself off now, though, because I'm not in prep.
There's coffee and ice cream outside, guys, so you can wake up. But you have about 5-10 minutes. Right behind the coffee. Okay, Steve, I'm gonna put you back for a little bit so we can start. Otherwise, we won't ever do. Okay, next we have Steve. What was the last name again?
Who's Steve? You have 4 minutes though, I'm not starting.
Okay, and he will presenting his talk, Computer Vision in Your Pocket, Exploring Phone Photos and with Embedding. Sorry.
All right, here we go. So, source, virtual environments, photo explorer, bin. The original question I was going to start this whole discussion with is, how many of you have actually done computer vision stuff before? A little bit? A lot? Then you can be my fact checker. Remember, I'm assuming that this audience, almost nobody had done computer vision. And the closest they've come to like machine learning neural network stuff is I played with OpenAI and it gave me crappy answers. That's about, and maybe you've seen some of the talks today, but that's about the extent of knowledge, I assume, for most people. So, app launch, oops, sorry. Start this up, we get our slides going. Restore, let's see if it restores just what I wanted. Yep. This is going to be slide deck for today. I have one more thing to launch before I can, and we'll probably have to adjust the font on this. I didn't get a chance because I was chatting. This will be our code for today. So there will be code. Most of this will be code, actually. Good. That font is definitely too small on the left side, correct? Yeah. I don't know how to increase that font easily, but I think I know how to increase this font easily. Or I don't. Okay, that's the one I actually really care about. For those in my age group in the back, is that readable to you? I don't know if you're really in my age group and you've got glasses on. Dude with the yellow, the Schroeder hat. Is that Schroeder or Charlie Brown? Can you read it? Charlie Brown, sorry. Can you read it? What did he say? I can't touch that stuff. They won't let me change the brightness. I can't touch anything. And I've got a high contrast theme and they say, do not turn off the lights. Change the what to a blue cyan? The theme? All right, we'll go with the theme. I'll change it, but then I think other things are going to get bad. This is never ending. You want me to do like that? Is that good? Oh, I love when we get so much agreement. Now I'm probably over on time. All right. That's good. All right, we don't need that. Let's go to our slides. Let's get going. You guys are so distracting. All right. So here's the talk for today. Computer vision in your pocket. My goal with this is I think LLMs kind of stink. They're interesting, they're great, they're awesome, and at the same time they really stink, and I think they're overhyped, especially right now. There is an area of machine learning that is actually, if you actually want to make money with computer vision, with AI, which is not AI, I would say you should look at computer vision. There's a lot more that you can do, and you can actually make real money right now doing it, or real good use cases with it. So this is actually a way of introducing you to that stuff via something that's, I think, accessible to a lot of people, which is the phones that come off of the pictures that come off of your camera on your phone, right? This is not, I'm not going to have anything fancy in terms of the images I'm working with. These aren't technically off, the pictures I'm going to show you aren't technically off of my phone. They're technically from my bigger cameras that I did. This whole project started for me because I like doing photography, because most of us here probably do as one of our hyperfixations or hobbies. And I wanted a better way to look at what my pictures had and what it was telling me, like finding the pictures I actually cared about rather than all the garbage. That link at the bottom, which I will repeat at the end, is this slide deck. Okay, so you can take a picture now, or you can wait until the end and take a picture at the end. If you decide you want to save the bits. That's me, I'm Steve. If you couldn't tell, I'm a very informal speaker. I want questions while I'm giving the talk, not at the end of the talk, please. Chances are, if you don't understand something, there's about 5 or 6 other people in the audience at least who don't understand it, and I'd rather catch it then. This is the GitHub repo for today. Not all the code examples got done in time. I'm, again, ADHD overambitious. So there's a bunch of code in there, but not all of it's filled in. I'll be filling that in over time, and you'll see the exact code I'm using today. And I made the repo in such a way that once you've loaded the pictures up, everything else you do from that point on is generic. So getting your pictures in is the thing that you'll have to do with yours, but it's pretty easy. So the goals for today are teach you some very basic ideas in computer vision and transformers. And like I said in the beginning, we'll ask again now, how many people here have actually worked with computer vision, done stuff with computer vision? Yeah, that's what I figured, a few. And one guy claims he's an expert, or he's done a lot, so he's going to be my truth teller. I want you to get hands-on in the sense of like actually seeing it done. With seeing some of the stuff, you can pull out some of your photos. And I would hope we're going to have some fun along the way, because if nothing else, I don't want you to fall asleep, right? So that happens a lot in talks. So the goal is not to have you fall asleep in the talk. So first things first, let's get going with the real stuff. Embeddings. Have you guys heard of embeddings at least today? Does everybody have heard the term at least? Yes? Do you understand what an embedding is? Okay, so that's what I figured. Most people are shaking their head no. I'm sure there's people who would shake their head yes. You can check your email, but no YouTube videos, please. So embeddings are handling a problem of turning things into numbers. That is what an embedding is all about. I'm giving you some motivation for why we need it with it. You're going to start with unstructured data. And unstructured data is challenging for computers. What's an example of unstructured data? Pictures. That's too easy. What's another unstructured data? File system. Yeah, that is, but it's kind of whatever. Yes? Right, so pictures, like, we're talking about pictures, lots of pictures. Text, right? You should know unstructured data is lots of text. Like, we're fine with a sentence or a couple words, but if I take a book, there's no structure in the book except there's a bunch of words in it, right? What's another example? Audio files, yeah. Would someone say speech? Is that what someone just said? Good call. Audio files. There's a lot of data in there, but it's not structured. It's not easy for a computer. So, like, for example, if I tell a computer is 2 less than 3, the computer says, I know what to do with that. That's great. I'll flip some bits because some OS guy or some low-level guy figured out, or gal figured out how to do that. But if I say, is this kitten less than this kitten? Or is this kitten cuter than this kitten? Or anything like that, the computer has no idea what to do with that. Or are these 2 cats? Right? About the only thing computers can do really with images natively is, are they exactly the same? And if not exactly the same, where are the bits different between them? That's about all a computer. To a computer, a picture is a big array of numbers and has no information in it other than the numbers that you see. And so our problem is how do we get the computer to actually be able to tell us something about these pictures, unstructured data? So this applies, all the stuff I'm going to talk about with the embeddings and stuff, this applies to text, all that LLM stuff as well, and embeddings from text. So the answer is neural networks to the rescue, right? And so what ends up happening is, to create an embedding, what you do is you take your matrix of numbers, or whatever it is, like in this case a picture of a kitten, you put it through the neural network, a deep one in particular, usually, yes, deep one, and what comes out the other end is an array of numbers. Okay. So you're like, great, I got an array of numbers. That array of numbers, the neural network is supposed to learn features inside of that image, and that array of numbers is supposed to encode some sort of information about those features in that picture. Does that make sense? Those numbers typically tend to be floats. Even though I put a whole bunch of ones in here, they typically tend to be between -1 and +1. Is usually what I've seen. They can be stuff like this. They can also be integers. That's a whole nother discussion. We won't go into that today, but just think of it as there's an array of numbers, and it's going to tell you that number encodes stuff about what's inside of it. What's another thing that we do like this with unstructured data? This is a Linux group, so you guys, I'm from New York. So when we use guys, it's gender neutral. When we use it amongst ourselves, so I'm sorry, I try to work on folks. So you folks, what's another way that in Linux, what do? What's another example of this? It's really simple. You do it all the time. When you download a package, they tell you even though you're supposed to and you never do it, but what are you supposed to compare? The hash, right? The MD5 hash. An MD5 hash is the same thing as an encoding. I've taken some big unstructured data, and I've turned it into an array, a string, of numbers that says something about that. Right? That's an encoding process. How many of you work in geo? Does anybody here work in geo stuff? Nobody? Yes? You do? Okay, now you're on the spot. You shouldn't raise your hand. Okay, so in geo, what's a process where we take some unstructured data and turn it into a two-dimensional vector? Yes. So he's basically saying geocoding. Have any of you done geocoding in any of your little map apps or anything like that? I have an address. Hey, Ryan. Sorry, Ryan and I used to work together a long time ago, and I didn't notice he was here. So, and Ryan has used my app that does that kind of stuff as well. So geocoding is the process of taking an address and turning it into 2D coordinates on a map, right? A computer, if I said whatever the address of this is in Pasadena, California, and I feed that into a computer and I said, where is this on the map? Natively, it can't do anything with that. So geocoding is a process of putting some unstructured data, an address, and turning it into coordinates. These are all examples of ways. In this, we have a particular one, which is the neural networks. We good? We're going to go over this more. You don't have to totally get this yet. There'll be more talk about it, all right? So this is the part where I'm going to teach you some computer vision about actually what's going on under the hoods. Have you guys heard about those embeddings with text? Were you at the RAG talks? Any of the RAG talks have to talk about that. Because you need embeddings to do RAG, Retrieval Augmented Generation. Right? So what's actually going on under the hoods with this is, and this is particular to computer vision. Remember I said there's a neural network. So you feed in, I'm supposed to stand here, but they can't control me. So is this a pointer? Yeah. So what you do is you start with your image and you feed it into the first layer of the network. Right? And then that network, and everybody understands basically what's happening at the most basic level. Each one of these nodes in the neural network is a nonlinear regression equation. Does everybody know that? Yeah? No? I see two heads. No, you didn't know that. Good. This is really, really important, especially for all this LLM bullshit about how this is intelligence and it's a hallucination, and it's none of that. This is a bunch of regression equations here, and we're going to be basically fitting those regression equations through some sort of fancy math to give us the output that we want. And so what's a hallucination in real life? It's an error. These are predictive models. It made a prediction error. That's all it is. Yeah. Yeah. At the end, I'll show you. We're getting there. You jump the gun. You jump the gun. Hold on. So what's happening? I'll get to that one. Ready? So the image goes in as all this. We start going through the layers. And typically when we do a prediction, what comes out at this last layer is our predictions. Right? At the last layer, this would be this might be something like woman, cat, dog, what's the weightings on those, and tell me what the thing is that I've actually got coming out. Usually what an embedding is, you drop this, and you just give the output of this last layer. The numbers that, you might do some standardizations on it and stuff, but it's basically the numbers that come out of this last layer in the network. You skip the last level of the neural network, and you just say, just give me the numbers. Give me the numbers here. So the number of nodes in that final layer of your network is generally the number of numbers in your output vector. Okay, does that make sense? And why is that thing important? Well, so here's what's happening as we move through the layers. For vision, I don't know, I think on text it's much more black box. As we move through, here's what's happening. At the very beginning layers, the network is going to start picking up on like really basic features in the image. Have any of you done photography or image stuff and run filters over your images, like an edge detection or any of that stuff? And you always have to pick like a whole bunch of things, like what's the size of the kernel, all that other stuff when you're doing that. The neural network is learning that on its own in that first couple of layers. And it starts picking up on significant features like lines, color gradients, things like this that are different between your different images. Then as it moves, those features become the inputs to the next layer. So that next layer can start putting things together. So in this case, it's starting to put things together like eyes. Right? It's starting to put together features that it will find in the images of this face that are conglomerations of, edge detections and stuff like that. And as we keep going, it's putting together more and more layers of that image. And so by the time we get towards the last layer, we're starting to put together faces, right? And that's just if you were doing like a face detection algorithm or telling people apart algorithm, right? But this is a simplistic way of understanding it in a case I think everybody understands. Does that make sense? So as you move through the network, you're actually starting to put more and more features together to get to the things you want to predict. And so that's what's happening when you're teaching this network. You're telling it, start finding the features here that are most important along the way to getting to the prediction I want. And so it gets really good at those things. Does that make sense? So what should happen at the end is this embedding layer has captured the features that are most important that we were using to do predictions with. So those numbers represent how well are we putting together those kinds of features. So that's what it means when it's extracting features from the images. Does that make sense? You can get embeddings from any of these layers you wanted to, right? You just have to basically say, don't go to the next layers, just give me this. Does everybody know what fine-tuning does? Do you know what fine-tuning is? Yeah, and there's lots of different ways to do it. But so this is what they say when they're fine-tuning. You get some big foundational model where they gave you the weights, which was very nice of them. They don't have to do that. But they gave you this whole neural network. They give you the weights for it. And basically what you do, you chop off this last layer of their network that does the predictions, and you recreate a bunch of new nodes here and get all of this stuff to start predicting your nodes. Right? Like if this was like a dog training data set and you could chop this off, put a whole bunch of different cat classes to predict really well at cats. And it would keep all of this information that it had learned about putting features. I think this is everybody kind of wants to understand these terms. Is that should I keep doing this kind of stuff? Is it helpful for people in the audience? Okay, good. Yes. Excellent. You win a prize and a medal because you asked a question and you're the first person. Go. Oh, yeah, right, he did. Sorry. No, typically, the embeddings are the output from only the last layer. Because all of these layers go into making up this layer. Yeah, what you're assuming is the pathways all the way through that make it such that the number that comes out of this last layer is the best at predicting what you want. So you don't actually need all the other weights coming out, the outputs from all these other ones, because they all get put together at this last layer. Does that make sense? Yes, the outputs, not the weights. The weights are just how we translate numbers into another number. What we want is the output from that last layer. Yeah, so he's bringing up is forward and backward data going backward. Yes, that's all part of training. We're not going to talk about that. Let that wash over you. Training, when you're training this, data goes all over the place. It's a lot more complicated. This is one of the reasons why, can I give an LLM thing for a second? Okay, this is why when I tell people when they start with LLMs, start with RAG rather than starting with fine-tuning. And the reason is, to do RAG, you just pick a model, you get the embeddings out, and then you do some similarity search. It's very easy, as you'll see today, to calculate embeddings. To fine-tune, you actually have to have like the same infrastructure and the same kind of knowledge in place that went into training the entire model. Because what you're going to do is train this neural network on a new layer, right? So if you're just getting started, don't start with fine-tuning, is my guess, to see if your problem even works, okay? That was an aside. Are you ready? Next slide. Are we good? Okay. And so this is me talking more a little bit about where the embeddings come from, right? So there's the puppy. We do a whole bunch of final stuff. There's the last layer. We drop the class probabilities, and we just take this last layer's outputs instead. That's the embedding, okay? Everybody pretty clear on that concept? Okay. So embeddings are used all over the place, and I think they should be used more. So then what happens is, so you're saying, okay, great, I got this vector of number. What does that number vector actually represent? That number represents the features in that image, right? I'm doing it here in 2D, but if you have like a 5 to 12 dimension, like you've heard of the vectors that come out of like a 512 or 1024 in length, those are the coordinates in a 512 dimensional space. Visualize that. That's why I made it 2D, right? But basically what that's saying is each one of those numbers is a coordinate. And if your model has been trained well on data that fits well to your use case, coordinates that are closer together should be similar images to the images that have coordinates which are farther apart. And that's a big if, though. And I didn't get that part of the demo running because it was some cutting-edge code that my coworker couldn't get working for me. But there's two parts that go into this, and I'll talk about this in a second. There's the model, and that's what everybody seems to get excited about, right? Like, when you read about, oh, I got better performance, and you go look at this model's better performance, and it's like 0.5 better performance or something like that. And then there's also the data that went into training that model. And it turns out that the data going into training the model can have a much bigger impact than the model and the architecture that you choose. There's a whole other talk I give, but basically you can take 10% of the data, duplicate it, and your model will get like 50% performance compared to what it got before. So you could put a whole bunch more parameters on, you can get those fancy GPUs, you could train it forever, and it's still not going to do any better. So which is why if you listen to a bunch of podcasts about this stuff and then people say, oh, should I get a bigger model, or should I, if I had $1 to spend, should I spend it on a bigger model, or should I spend it on cleaning my data? They always say clean your data. Good quality data, I mean, how many of you took some sort of statistics? You all took it, right? And what did your statistics professor tell you about the quality of data? Garbage in equals garbage out. And that hasn't changed because remember, we're just doing a whole bunch of regression equations. So you can put as many parameters on there as you want. If you're feeding in garbage data, you're not going to get good results. I was training a satellite model the other day, image processing with garbage data, and the model, its learning plateaued at like 0.1, when it should be at like 1 is what you're going for. And that's because the data was garbage. So pay a lot of attention to your data. All right, so this is a whole thing to say, hey, things which are more similar should be closer in this coordinate space. Does that make sense? And that's how RAG works as well. Sorry that I'm going off image stuff again, but that's how RAG works. What you do is you make embeddings for all of the documents that you have, and no matter what, data going into an embedding model, it always stays the same. If you put the same data through, it never changes. You always get the same embedding out, right? And so what you do is you make embeddings for all of your data, you get the user's query, you embed the user's query with that exact same model. Does that make sense what I just said to people? So you have an embedding model, you've embedded all your data, put it into a database using that embedding model. Clear? Your user asks a query saying, hey, usually you that query straight onto OpenAI and say, hey, OpenAI, or whatever you use, or Claude or Llama or whatever you're using, give me the answer to this. Instead, what we do now is we say, take that user query, run it through the exact same embedding model, now search the database, find all the stuff that I have that OpenAI doesn't have or Claude doesn't have or whatever, add that into the user's query as context for the LLM. So that what you've done is you've said, here's the original, and then send that on to the last model. And you're saying, so here's all the stuff, here's the user's query, and hey, for context, here's all the stuff that I know about that question, so you can restrain your answer to that. That's RAG in a nutshell. Good? Sorry, was that good? You liked it? Thank you. Even though it's not computer vision, I hate how much people are like glorifying LLMs and like RAG and making it like this. If you're not in the ivory tower and you're not super smart, you don't know you can't do this at all. And it has nothing to do with smartness. Okay, so then the question is, I'm going to show you some pictures actually of embeddings in 2D space. These are like 512 dimensional vectors. In one case, it's like 2K dimensional vectors, but I'm going to reduce them to 2-dimensional space. Because can you see in more than 3 dimensions? Like, can you visualize that in your head? Can you understand it? I can't. 4D, I kind of can. You can take a cube and kind of move it through space, but that's about it, right? And so we need some way to actually make it decipherable to us, to see how things are close. And so there's a bunch of different ways. A bunch of you said you took stats. Does anyone remember principal components analysis from stats? You do? You don't? Shame. Did you learn about it at one time, though, and you forgot it? Dude, we're about the same age. I did PCA out the wazoo. So what PCA is a dimension reduction technique. You have like a table of data is usually what you had, some sort of spreadsheet or something of data, and you wanted to have less dimensions to put in your regression model and you didn't care about explainability. What PCA does is it takes that cloud of data and it straight linear algebra. This is not a statistical technique. This is straight linear algebra. You just basically take the eigenvalues and the eigenvectors. Everybody remembers those exactly, right? Totally. And then what you do, basically what it's doing is it finds, in this cloud of data, what it did is it found PC1, principal component 1, is an axis that captures the maximum amount of variation in that data. Does that make sense? And then it says, okay, given that, I now need to make an orthogonal vector relative to that captures the next most amount. And so that's what it's doing here. And then what you end up is you can replot into this new principal component space, and you've only got 2 dimensions rather than 3. And it's trying to maximize variation captured among the 2. So its goal is maximize variation. What we're going to be using today is something called UMAP. I still don't understand it exactly. It involves fuzzy logic and Riemann topological operators. Everybody's worked with those, right? So, but basically what the idea is it's trying to do is it takes the multidimensional space and it tries to, as it's bringing it down in dimensions, it's actually doing model fitting. This is not a linear algebraic technique. This is actually a model fitting technique. And what it's trying to maximize is keeping closer things close together as it reduces the number of dimensions. Okay? And that's what we're going to be seeing today. It does way better at the kind of for embeddings than PCA does, because it's actually like aware of the data and trying to keep things in a certain relationship. Okay? I don't think most people need to know this. I just wanted you to kind of understand it at a very high level. The important part about this, though, is that changing the data set, either the samples in the set or any of the values, will change the coordinates. So while I said embeddings doesn't matter, no matter what, the embedding will always be the same if you put it through. The coordinates will not be the same after this if you change anything about the data set. You have to rerun the coordinates if you change anything in the data. That was the big take-home message. Okay? Embeddings stay the same unless you change the model. 2D projections are sensitive. All right? That's it for slides for now. Everybody good? You want more talk? Sure. No. Everybody's starting to be like, okay, that's enough. Let's just show me something interesting. All right. So let's see. Okay. Yeah. UMAP is not even anything like that. It's PC. So the question was, when I interrupted, he didn't get all the way to his question, but I think his question is going to be, PCA is like a matrix manipulation technique. Is that the same thing in UMAP? And the answer is no. UMAP is a statistical fitting technique. You're doing gradient descents and all sorts of stuff as you're trying to find the right coordinates. Okay? Quick geo thing though is, what's another place where we do that kind of dimension reduction in geo? Kinda, you got to be a little bit more specific to get credit for that one. Not exactly. Okay, what shape is the Earth? Spheroid. It's a spheroid. It's not a sphere, but it's a spheroid. And what shape is a map? Flat, 2D. So when we create a map, we are projecting from 3 dimensions down to 2 dimensions, exactly like that. In the case of maps, it's formulas, not statistical fitting. And that's all those different maps. Trivia, cocktail party, people love it. All right. So for most of the stuff I'm going to do today, I'm going to use the visualizing from the company that I work for now. But I love this stuff, even before I joined there. And like the hard part for me of working with this stuff is not playing with the data all the time, just because it makes it so much easier. So what we did, the example 1, I'm not even going to walk you through it. But example 1, when you go to the source code repository, actually just loads your data into the platform. And so the only thing I'll show you here is, because some people will give me quizzical looks, fine, I'll show some of it. You give it a directory, and you make a data set from that directory. And the data set is the thing that we work with, right? And it's like 3 lines of code. And in this case, there's 2 examples I gave you. One is, if you don't care about any of the metadata in your images, you just like, give me all the images and put them in the data set, that's fine. For me, because remember I said this was my photo collection, I actually wanted to see if I could do stuff with EXIF data. Does everybody know what EXIF data is? Is that metadata associated to images? So the second example actually shows extracting the EXIF data from the image using EXIF something, and then attaching that to the sample inside the data set. Okay, so when you go back, that's what you're going back and you're looking at. We don't have to talk about that part. Everything from here, so remember I said it was generic? Everything from here on just assumes you have a data set. You don't have to do anything else. A data set of images. Good? Okay, so nobody said no, so I'm assuming the answer is yes. That's what I tell my kids. Not that you're my kids. Yeah? This has nothing to do with neural networks yet. Good question. Did anybody else have that problem? Yes. See, his heads are shaking. This is exactly why you should ask questions. This is just loading the data set into the platform. We haven't done any fancy machine learning yet. You're loading the EXIF data because you're going to be using it. And it turns out I don't. Okay. But I left it in here as an example in case people wanted to do something with their own images. I could have, for this case, this 1-liner or this 2-liner would have been enough. Just take. I'm sorry. I know your time is precious. All right. So the first thing that we can do, and I don't know how many of you have done this, but I need to make this bigger. Oh, come on. Which one is it? There it is. Can you see it in the back now? Good? Okay. So we have these things. We have things called plugins, and some dude wrote a plugin. In this case, it is a dude. He wrote a plugin that actually computes problems with images. Just things that I always want to see that I can never get out of, like Darktable and things like that, which is things like, is the brightness off? Is it blurry? Although the Laplacian filter is terrible for that. But like salt and pepper and things like that. So once I've computed these statistics, I just say, hey, go compute these statistics. That's what's happening. I load this, I say compute it, and it automatically gets associated with my data set, and then where's my data set? It was supposed to have launched. Where'd it go? Sorry, you can't see this part. I forgot to start my Mongo and Postgres instances. And what am I using? I know I'm using Docker, but I'm on Ubuntu, so I would have rather used Podman. Docker, start, photo, or Mongo, and then, but the beauty is, with containers, it's super fast. All right. Now I can start up the platform. Sorry about that. So I'm launching the app part of it right now. He hates that I'm using Docker and not Podman, and so he's leaving now. He goes, oh, you do? Yeah, great. Yeah. We don't need no daemons. And of course, it's running a lot slower now. 51 is the platform that we do. It's you pip install it, and then it's got like a bunch of. I don't know why it's not loading, which is not fun for me. Because it was working. This is what I get for rebooting my machine. Yes, I did. I know it doesn't matter. It shouldn't matter. I don't know what it's doing. Hold on, let me try one more time. I know, exactly. This is the excitement and the horror. Yeah, it just did this before, too. Rats. It didn't shut down when I just told it to shut down, or it's doing something weird. And it just did it before, and I don't know how to get it to stop. And I did this, for those that are here, we're at Linux, so I can do ps-auxw 50, and then I grep for 51. And you can see, oh, there it is. It's bound on that port. So and then I say, actually, I should do this. Kill -9, but I'm a little worried about this because I don't know if it has a lock file somewhere or something. 108.92, right? And then you would think, I do this, and it should work. What's that? Am I using the right? There's no virtual environment. This is just all running right here. And I don't know, I've rebooted to exactly get rid of this problem, and I don't know why it's not happening. So let's see if we can start it another way. You're like, this is a great demo, Steve. This is a ton of fun, thanks. Import 51 as foo. fo.launch app. Did I spell it wrong? Yes. Pair programming prize for you. And it's probably going to give me the same error, but. Anybody have any other ideas about how I can kill that connection to that socket? How do you grep for, is it LSFOF that tells you sockets? Wait, I'll take his because he's closer. Nope, here, go. Netstat-AMP. Could I grep for 50? Oh, this is the best part of the show. He installed Netstat live. I don't know. It was working. I shouldn't have rebooted. Just too much. Just app install. Did I put get? Now I'm. Oh, so you sent me down the wrong path. It's all your fault. Did you? Is that what you said to start with? They said the wired network here is fine. In the meantime, any other suggestions about how to kill that thing? SS-T-U. How about grep? No? Grep 5150. That's where it's going to be. Maybe it's dead now. There's no way I'm going to be able to look. Oh, there it is, 5151. All right, how do I kill that? I don't want that anymore. That's the problem right there. These two. These three. I don't know. So reboot. Control-Alt-Delete. What? The 5151. All right. LSOF, just like that. -A, that's a good idea. And grab 5151. No. Okay. This is like turned into the Linux contest. You thought you were going to learn about computer vision. That's not helpful. Why is it taking so long? Do I need to be sudo? Oh, there it goes. So it's all, this is the one I need to, oh no, that's not the one I need to kill. That's the one I need to kill. Is that right? What? Kill -9. 10936. Like that? Yes? Linux? Yes. Good. If it doesn't work, it's your fault. All right, here we go. Yeah, I killed that. Yeah, but that doesn't, don't clap yet. We'll try again. I'm thinking there's something stuck somewhere. 51, app, launch, not lunch, launch, photo, album. Well, I said I wanted us to have fun. Isn't this fun? No. That's good. I'm not touching anything. Why isn't it? That's bad. It's taking too long. No, I just did that and it didn't fix it. Then I'm screwed. No, we're screwed. It's just all screwed. Now I'm trying to think of how I'm going to rescue this demo. What? No, I'm using the local network, but it's all running locally. Maybe if I unplug from the network. What? I know, but maybe you never know. It's Ubuntu. Take localhost down. I'm unplugging. That's going to totally fix it. Didn't fix a thing. Yeah. It's not, Something's going on. Something's lost, logged, corrupted. What? It's still loading? It shouldn't take that. That's like one of those things when it takes that long to load. It's probably listening. Yeah, I do now. Because some great guy told me to do it. What, sudo netcat what? Localhost space, and he's blah, 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 blah. What? It's 5151. Yeah, 5150. Temple of Syrinx. What? So it's up. I think there's something hosed in the database. No. The fact that it was pixelating meant it knew it was bringing up the app. I think something got hosed in the Mongo database underneath. I know. I can tell you internally on Slack every single. Oh, I shouldn't say that. I'm like, Postgres does JSON. Let me try to think about how I'm going to try to rescue this. What? No, I can't. You know how long it took? So I'll show you. I'll walk you through some of the code, and I'll tell you what you would have seen, and you'll imagine it. I'm not running anything else on Docker, but let's see if Docker, maybe it's down, you're right. Maybe let's just do Docker PS. Nope. They're all up. Restart Mongo? Sure. We got nothing but, yeah, we do. Do you want to see a little bit of the code, though, at least, just so you can understand, like, what's going on, rather than me troubleshooting Linux? And then we can talk about, I can try to get it to work? Okay, let's just do that. Right, so you would have imagined you saw a number that showed the brightness, and you see a grid of images? Yes. That code right here, it goes through for each image and calculates the brightness for each image, and then what you can do, imagine, if you will, a carousel of images and then a selection on the left side. And you can pick the brightness field, and then you can filter based on the brightness value, and it'll interactively change the images that you can see. So it becomes very easy to see, these images are too bright. I want to delete them from my data set. That kind of stuff. Okay? You can also do like a plot where you can show, that's enough for these ones. Let's get to the real stuff. This is not any, this is just basic OpenCV stuff. This is the interesting parts. So in this one, I'm calculating embeddings. So what's happening here is, 51 comes with a model zoo. So I use those because those are just easier. We've taken a bunch of the most popular models and put them in a format that works really quickly inside of our platform, but you could do this with external models as well. This is too small. So what's happening here is, in this one, I'm loading the ResNet 18 model. This is probably one of the simplest computer vision models that does embeddings. Okay? The next line is I'm loading OpenClip. Have any of you heard of OpenClip? The vision people should say yes. OpenClip is what's called a multimodal model. Do you know what multimodal means? Some people do. You want to explain it? Don't say multi-modes, that doesn't count. Multimodal in this case means it handles both text and images at the same time. That model was trained with images and captions for those images at the same time. And so it's doing LLM-like stuff with the text, and it's doing image-like stuff with the images, and it combines them together. So you can do things like ask it using text, show me all the images of, is this an image of a cat? And it will respond. Or give me a caption for this image. Some of them will give you a caption back out. All that kind of stuff. So that's a multimodal model. What's really great about a multimodal model, if you are going to get into computer vision, is you can use them as your first pass for doing image classification. What's the typical process when you do image classification and you're building one of these models? What do people spend millions and millions of dollars on every year? Annotations. You know, remember like Meta, all those poor people and I don't mean financially poor, I mean like I feel bad for them poor, like in Africa and stuff, who had to look at all the horrendous pictures on the internet and say safe, not safe, or I'm showing you like this is a knife, this is a gun, like that's annotation, right? These models, again, it's all about data. You can't just give it a picture. You're training the model, so you have to say, in this picture, here are the following things, or this is a safe image, or this is a porn image, or this is a whatever image. Someone has to go through and do all that stuff. Because the OpenClip model understands human text, and you knew you had a certain number of classes you wanted to classify for, let's just say you wanted to classify, give me some examples, safe for work examples. Anyone? At work, think about what you do at work. Is there anything that you do with images at work where you'd want to have classes? Not safe what I do actually at work. What? Laptops? Yeah, so you could say, what model laptop is this? Right? If you or you could say some laptop or a desktop. Yeah. If the model's been trained on it. What I typically do is say, is this a cat? Is this a person? So you have a question, what is this a picture of? And then you give it an array of classes you want it to find, and it goes through the images using that text and generates that last layer of the neural network model to predict this is this is a cat, this is a that. It'll actually attach that. And why is that great? Because nobody has to look at the image to start with, and you've already got labels already put on the image. It's really onerous going through every single image and writing it by default. This is actually a good use of machine learning, right? It's the same reason I like LLMs, because I think they're a good text calculator. I want to write this thing, but the white page is scaring a lot out of me, and I don't want to write, here's the outline I want, give me a first draft. And it gives you the first draft, and then you can do stuff with it. And that's the same thing here. It can give you a first draft on your labels, and then you can proceed to correct them. So that's the really great part about these one-shot open ones. The other one is there's a new one-shot model that just came out from Apple, and I'm computing the embeddings using that. So here, this compute visualization actually says, it does two things. Compute visualization calculates the embedding, and then at the same time, also does that two-dimensional reduction. So what comes out at the end is there's a field or there's a brain key that says this is where it is in the database, and you can actually do the embedding visualization. So that's all it takes to calculate embeddings, which is why I said it's super simple. And this isn't really just on our platform. It's pretty simple in general to make embeddings, okay? The nice part here is it's just integrated and you can start. And then what comes out at the end of this is you have a 2D plot on one side with a whole bunch of dots in clusters. Some clustered well, some clustered not. And as you circle the clusters, the images change. And you notice this cluster is cats. This cluster is stars. This cluster is motorcycles. So you actually get to see where it's actually making what those embeddings correspond to in your images themselves. So what was exciting about this for me is I could find clusters that are like, oh yeah, I took a lot of pictures of monkeys. Like, I like those pictures of those monkeys. Oh, there's a really good one. You can also see when there's a lot of mixture. Oh, there's monkeys, and there's birds, and there's kids climbing in trees all in this picture, these pictures in this cluster. This model is not doing a good job of picking out the things I want. I should either retrain on different data or use a different architecture. Yeah? It's not going to tell you if the... So that is a totally different question. So what we're doing here is classification. What you're talking about is what's called object detection. I have slides for that. Do you want me to keep going with a little bit? And I can get to it. Do you want me to keep going with the text, for the code for a little bit? Or is this code, like showing this code, not exciting? Some people are like, this sucks. Other people are like, show me some more slides. Keep going a little bit. Okay, so that's it. That's all you have to do. What I did in this last one, which you can also do with embeddings and UMAP, is you can just concatenate embeddings together, right? They're just coordinates for that image. So you can actually take the ones that come out of ResNet, which has no multimodal, so it has no human concepts really in it. It's really just looking for features, and you can concatenate that embedding with the ones that come out of OpenClip. If I could have shown you this, OpenClip does really good at picking out stuff that correspond to what humans think of, and classifies them, puts them closer together because we gave that semantic text. You put the two together, you concatenate them, and then run UMAP on them, and you get the benefits of both. You start to see more structure and more semantic meaning in some of them. So that's what's happening in those last two. I'm calculating that two-dimensional reduction by putting those two embedding vectors together. So that's a fun, really actually interesting thing to play with. Yeah? So the question was, the model probably assumes it's one dimension. There's a set dimension for the images, and what happens if you feed a bunch in? You don't. Basically, there's submodels that can handle multi-dimensions. Some, they're trained on, like, let's say a 224 by 224 or 336. You have to feed in a 224 or 336 by 336 image. And then under the hoods, it can handle that in one of two ways. If you don't, you can either just crop. So I'm taking the center, you don't get the rest of the stuff, or I'm going to rescale your entire image down to that. So you can do it beforehand if you want to. Some of the models they may be trained on a certain size, but they can handle any size image going in. It's just what ends up happening is the bigger the image you put in, the slower it becomes, right? And the model probably won't be able to pick that stuff out because it wasn't trained on an image that big. It can't handle as much of that information. Yeah? So the question was, when you go from 200 dimensions, like in that embedding plot, down to 2, is accuracy reduced? Has to be. It's the same way, yes, it has to be. So the thing that you pick with the dimension reduction is, what are you trying to preserve as most? It's the same way when I like to talk about maps, because A, I'm a geo person, but B, because I think people have already encountered this. Like, we all remember how, like, the Mercator projection, the one where all the lines meet nice and square, and Greenland looks bigger than Africa, right? What that map projection, when it's going from 3 to 2, what it's trying to preserve is direction, right? Because all the lines of latitude and longitude meet at right angles, right? But there's other projections where you can say, I don't care about direction. I'm not trying to navigate with this. I'm trying to retain area. And so you use a different projection formulation. So the same thing with here. So that's the reason why UMAP is kind of a better than the others. It's basically saying, hey, you want to keep like things near like things as we go down in dimensions, and I'm going to just try to statistically find the best way to do that. That's what UMAP is doing. But yes, you're giving up something because you have to. There's just no way to do it. The advantage is you can actually visualize it. It does the reducing dimensions. That's just for visualization purposes. It's not. I mean, you could use that two-dimensional vector afterwards, but I wouldn't. If you don't care about visualization, I really wouldn't do that dimension reduction, right? The reason you'd want a smaller vector coming out at the end is because you probably want it to be faster, right? You want it to, because the size of that vector coming out partially determines how long it takes. So like if you're running something on a phone, you don't want a 2,000 dimensional vector, you probably want like a 512. So you would just pick a model that only has a 512 output layer at the end, and a smaller model. Any other questions about that? We good? Okay, the next thing I was gonna show you, God, I can't believe this was such a cool demo too. Can we just check to make sure it just doesn't come up, huh? Whoa! It was because of her question. You get the prize. All right? Yes! All right, so as I said, doubters, let me show you, I ran those 3 embeddings. So now what I can, do you care about the brightness filter thing? Nah, yes? Come see me afterwards. I want to show the embeddings because that's way cooler. All right, so remember I ran all those embeddings. I'm going to open these side by side. So the first one we said was ResNet. So there's all the dots for all our images in ResNet. Remember, ResNet doesn't have semantic knowledge. So what is this cluster right down here? Oh, some pictures I took in Kuala Lumpur when I was doing a show there. And these are all just pictures of me taking pictures out the window. What's this over here? Oh, these are things on a grass field. Now remember, ResNet does basically does structured stuff. So I want to show you what happens differently though, because can everybody see that stuff well enough? Okay, so this is me in Tasmania with some sort of parrot in a field. This is my dog doing lure coursing. Did any of you done lure coursing with your dogs? It's freaking amazing. It's so much fun. And then they tie a plastic bag to a rope on a field, which doesn't sound amazing, and then they hook it up to a lawnmower engine, and then they zip it around the field, and dogs who are sight-focused and prey-focused run as fast as they can after that plastic bag, and it is the most amazing, if you like dogs, it is the most amazing thing to see. This is pictures of one of my son's field trips with a bunch of kids. How did the what? How did you know that those were all connected to the photographs? That's my guess. I'm just guessing. But that's one of the things the embeddings, I can circle that cluster, and I'm trying to say, okay, well, what connects that cluster? What might it be picking up on? It looks like it's some sort of grass with maybe a little bit of light stuff on the top, maybe, but I'm mostly picking up on that I think it's grass. It's here's a peacock, right? So we got a bunch of different things in the field. You'll notice what's happening. Can you see over on the right side? It's turning those dots orange, because I've selected them. Now watch what happens here. Let me pick a couple more, just to make sure that you see it. There's my dog, Hetty. She's so cute. And we'll pick a couple more kids. All right, there we go. Oh, no, there's Aya. This is the one that really likes chasing bags in the field. I changed that now. Remember, OpenClip was semantic, so it understands human concepts. And watch what happens to those dots. So those dots have now spread out, because OpenClip isn't caring as much about, is this grass in a field, what's the texture or the structure in the image. It's looking for things that are semantically related. So if I go over to this cluster over here, you can see this, it thinks are tents in a field, or something else with it's some green and then a bunch of this white, it's either a tent or a camper, some sort of camping thing. I don't exactly know. Embeddings don't tell you that information, right? They won't give you that. What's this? Oh, we lost all the other points. But so this is the difference between what I was trying to show you there was open, a semantic model versus a structural model. The other thing that I'm going to point out here is that both of these models were trained on the same data set. They were both trained on ImageNet, so the data that went into them is what enables them to figure out the different features that's going on. If I had trained these models on just a car data set, same model, but just trained it on a car data set, these would look like a mess. Because I don't have very many cars in my pictures. 5 minutes. Damn it. All right. So, it would have been a mess. So this is where data is important. Don't just think about what model you're using. Really pay attention to whatever model and whatever data it was trained on. If the model's never seen that thing, it can't tell you about that thing. Does that make sense? Right? Okay. So can I just show you the really cool things? Is that fine? Okay. So here you were asking about, here's the zero shot. Remember I said I could just give it a list of names and it could tell me stuff? This is me telling, I think it was either the Apple model or one of the others, using the ImageNet classes. So ImageNet has 1,000 classes in it. And I said, hey, take these classes and make one word per, tell me what you classify this into. And so it's making guesses. Let me clear this because it's not quite so exciting. It's making guesses about what's in here. So it says this is ImageNet does really well with birds for some reason. So it says this is a cuckold with 0.39%. It believes that with a 0.39 probability, right? But then if I go to this one, It says this is a balloon. My daughter would be so insulted by this. She is not a balloon, right? But the other thing you can see about it is it doesn't really believe it's a balloon either, right? And this is one of the problems with LLMs, very quickly. We force LLMs to predict words no matter what the probability is it thinks of that word, and that's what a hallucination is. It predicts a very low probability word, puts it in the sentence, and because of the way LLMs work, all the words following it are based on that really word it never believed in the first place, and so it goes down this really weird path. Designers of LLM output should show us color coding for the probability of that word that it's predicting, so that we could say, oh, it didn't really believe that word. There's probably something wrong in this sentence. Done. Anything else? This is not a wedding. This is the prom, even though it says groom and bridegroom. This is a prom picture. That's my stepdaughter, and she would be horrified to think that she's getting married. And then that's object detection. Right, so this is a different model I ran, which is for object detection. So rather than saying the whole image is a groom image, it's now saying, I found the following things in the pictures, and here's what I think they are, with their probabilities. So it's pretty confident those are all people, which it should be. And then it also found the cell phone, which I was like, whoa, I didn't even think about that. So it found the cell phone in the picture. And so these are the differences between classification, which is the entire image, and object detection, which is a harder problem. Why? Look at what's happening. Look at the difference between the two things. It has to find a bounding box, and then it has to say, oh, I think this is a thing, and now I have to think about what is that thing that I actually found, right? So this is a harder problem, but it's way more useful. Like when I originally did this project, I wanted to do probability of filter out images with people because I never turn those into professional pictures. It's mostly just animals for me. And so what I would do, I did a classification, and it really did poorly. One of my coworkers was like, well, Steve, you should have done an object detection, and if there's a high probability person in the picture at all, then just classify the image as people, right? Because it can actually go through and find people, as opposed to saying, here's an entire image, are there enough people in it to call it a people image, right? Which is a harder problem. Last thing I wanted to show, and this is related to the whole topic of the thing, is I did this. There's some other models that do text generation. Remember I said that they can generate captions and stuff? So there's, Janice, the new one from DeepSeek? Everybody heard of DeepSeek? Okay, they released a model. Yeah, even he's heard of Janice. That's awesome. Good for you. Or DeepSeek, at least. They had released a model that actually can do caption generation as well for images. And then there's another one called Moonbeam. I forget who it's from. It's actually a better model. But I said, give me one word to describe this picture, and only one word, right? And I didn't have to give it a list of classes. I just said, give me a word, right? This one, I had to say, here's a list of classes, put it in one of these classes. This is just give me a word based on what you know, and what comes out of that is, we'll start with the good one, which is Moonbeam. That is the word cloud for my images, right? Because I said, give me one word, it associated that word, and it's 3 lines of clone to generate a word cloud. It's 150 lines of very complicated code to generate a word cloud, but I took it on for you guys, and that's what we got, all right? So this is what, thank you. I prefer the Moonbeam one also because these are really nice words, but you can see that like I was the photographer for my son's marching band, right? Like that's a nice big word there, serene, lots of people together for marching band, nature, natural, joyful, of course, because it's me. Then we looked at the word cloud from Janice, and I have questions. Like, what does require mean in an image? So I can actually do this. I know I'm out of time, but give me one more second. So I can actually do this back in the interface over here. If I go to, let's clear that, I can say I'm going to make a histogram, and what I want to make it on is the Janice, where is it? Does anybody see Janice? Janice, image, answer. These are the answers that Janice gave me, right, for all the words. And I think this one was answering does not require reading text in the image. Band. I don't know where it came with require from. All right, so if I click on band, though, like I want to see all the band pictures, I think that word cloud's busted. Anyway, if I click on band, that's why. Do you see the reason why? It's just the first 200 results. But if I click on band, it should, well, never mind. No, it doesn't. It should have clicked over and clicked all the images that were banned images on the other side. But if I can't do that, actually, I can do it this way even easier. Forget the histogram. Where's the Janice images? Answer. Let's show them. And then let's say filter by Janice image. Answer. What was it? Require? See, it doesn't say, it doesn't have it there. Reading, though. What is that? These are all, oh, that makes sense. These are all people reading, right? Some in synagogues, some camping, but those are the reading images, right? So this is, the reason I love this platform, despite the fact that it pays my mortgage and my food, is I love doing this stuff with images. Like, I can't think of another way to do this with images. And so that's why I actually find this like, and it's open source, of course, right? And you can use it, and if you want to do it at a company, we have a Teams version that runs on Kubernetes and all that fun stuff, but I use it for this stuff, and I can play with all the latest stuff, and it's really easy for me to do things that would be almost impossible. I don't like matplotlib and in a Jupyter notebook and show me 5 images. Now show me another 5 images. Now show me another 5 images, right? Like I can easily scroll through and do all that kind of stuff. Finishing up the slides, if you want to, I had other stuff, but here's where I talk about different object detection techniques. Here's where 51 fits in quickly. You define the sensor and the business questions, and then you go to production, and everything in between, we kind of tie that together with that kind of platform. Enough? No more sales pitchy? Yeah? Okay. Teams. Nobody needs another chatbot. Nobody needs another chatbot. That's the biggest thing. So start working with computer vision. People can actually, you can make our customer lots of money and lots of interesting, really interesting problems, as opposed to, do I want to kill myself or not? There's interesting things you can do with just the phone. You don't have to go get, we have some data sets in there, but just take your phone photos. Like, you understand those, you knew why you took them, you knew what's in them. Just start playing. Like, that's the best way to learn this stuff, is to play, try out all the different models. Don't ignore your data. Don't ignore your data. Everybody gets all jazzed about the latest and greatest model, and it's not all that latest and greatest usually. It's the data that will give you a better impact. And I think this stuff is fun when it doesn't not start. Here's ways you can come hang out with me. This is the one I want you to do. Come join me on Discord, and you can hang out with us. And there's the link to the deck again, which also has the link to the repo. Move it on. Go back one slide. Oh, people were taking photos of this, sorry. But you can take pictures of this, but what are you going to do with that? I mean, you can say, Steve thinks things are fun. Woohoo! Go to the deck, and then you can actually see all that stuff. And you can click on the link. But sure, thank you. Thanks, everybody. Sorry about the problems. And thanks for the Linux tutorial. Thank you for the Linux tutorial. What?
Not a MacBook. Points awarded.
Ugh, Mac is my least favorite.
Does the embedding, when you compare it, I know in RAG, they use cosine similarity.
My lactose intolerance, but
takes them out into like the Central Valley. Yeah, that's what that is.
1, 2.
That's great stuff. Love it. Love it.
Is this your HDMI or?
Yep. Everything is yours. Sorry. Thank you for reminding me.
Obviously, training and retraining on the data is an issue, right? That's going to take time.
Yes.
Time is a limitation.
Yes.
Okay, so are there any optimizations? Can you layer models on top of each other, have a core model, stuff the results, the embeds into the exit in the images so that you don't have to retrain?
Yeah, or stuff like that. That's what we do with ours, right? Like that embedding, once it's calculated, it's like a hash. So you can put that embedding anywhere you want and reuse it over and over again. Because, like I said, as long as that model stays the same, that embedding never changes.
So how are these things to destructive transformations of images? For instance, you have maybe
Okay. So that's a good question. I don't know the answer to that, right? But basically what we are doing is computing a hash, right? And in the same way that like there's cryptographic hashes, which is like if any bit is different, they don't match. And there's other hashes which is like, they're close enough. They're probably the same image. Like you can do image hashing, which is like it's probably the same image, so I can have a few bits that are off, and I'll still call it the same image. You're going to have to experiment with that about like how much, because it's a lossy technique. You're going to lose information in the data. The question is, how sensitive is that model to whatever you altered in the picture? Does that make sense?
Makes sense. I'm thinking of using LLMs for image classification for like images from the Perseverance rover and things like that.
Yes.
You're going to have situations where you're experiencing different levels of light versus dust clouds, things like that.
Okay, so that's a well-known topic in computer vision, and it's what they call like illumination or augmentation. In computer vision, when you do computer vision stuff, one of the usual training techniques is you take your original training data set, and then you take each of the images and you change the everything in the image stays the same, except the contrast changes a little bit, or you skew the orientation, or you make it darker, or like they basically, if you're doing a good job of training, you'll take your original.
This yours?
Nope. It's all yours to use. When are you up? Right now?
Yep.
Let me get out of his way, and then I'll be out in the hallway.
5.5 minutes.
Yeah, that's okay. I'll give you some quiet. Thanks for your questions. Do you actually digest?
I'm a MongoDB community member, champion stuff. But if you have Mongo trouble,
I should have talked to you.
Yeah.
I don't know what that was. I have to talk to my team about why that happened. That's the first time I've seen that. I just moved. We used to use embedded Mongo. Well, we still do. Embedded yeah, you can actually start up the Mongo process from a Python process.
That's not embedded. That's just starting Mongo process.
But now I run it as a standalone container. Python's not starting it, which is actually better.
Yeah, to give you consistency.
Sure. Yeah. But I don't know what happened with that.
Yeah, I don't know.
Thanks for your questions, though, and your help.
But seriously, if you wanna
dig in on that.
If you wanna get better at Mongo or you have issues.
Yeah. Oh, thank you. Thank you. Sorry.
Okay, next we have Mr. Nuri Halpering, and this would be the last talk of the evening for us in this room. His talk is Vector Search Right for Me? So, round of applause for Mr. Halpering, please.
One, two. Yeah? Hey, all right. I promise you I'm not going to be as engaging as the previous presenter. So it's time to just calm down. My name is Nuri. I'll be speaking about some amount of vector search and trying to really answer the question, is vector search right for me? To that end, if you expected slews of code or fancy demos, you're going to be disappointed. But I am going to try to answer the question, is vector search right for me? Roughly speaking, I'm going to give an overview and understanding of what vector search is and what I mean when I say vector search. I'm going to compare vector search to traditional search, so we already have a preconceived idea of what search gave us before vector came onto the scene. So I'm going to do a little compare-contrast there. I'm going to talk about the use of vector search in what's called Retrieval Augmented Generation, RAG, for those of us who learned about that in the last session or otherwise. And I'm going to also talk about applications of vector or vector search as a notion that go beyond and besides RAG, because vector search is not, contrary to some belief, is not just for RAG architectures. It's useful elsewhere. And I'm going to also maybe talk about the layout of the land, vendorism, and some of where could this be found and how can I use it in my ecosystem kind of stuff. All right, so that's what I promised to do, should the gods of technology allow me to. So vector. What is a vector? We'll want to define it. We'll want to talk about, if I had a vector, how does a vector relate to other vectors? How do I deal with it as a data type? And we'll want to talk about efficiency at scale, because as it turns out, those little things about how to compare vectors cost quite a lot of compute time. So vectors. What are vectors? They're multi-dimensional scalars. They're a single buffer. They're an array of multiple elements. What are those elements? Numbers. What kind of numbers? Real numbers. So a vector, this is a representation of a vector in 2D space, and we can imagine that these are all 2D vectors. One element, the first element in the array containing the x value, and the second the y. And we can imagine that if we had space in the vector, in the array for 3 elements, I could describe 3D space, 4 elements, 4D space, and so forth and so on, into unimaginably complex spaces. So when we talk about n space, we're just saying, hey, a vector is of length n, 512, 1024, 384 for all numbers. I don't know why, but there are some embeddings like that. So that's what we're talking about. And vectors, when we look in 2D space, have a direction and an angle. Typically, they start at the origin because you only supply the x and the y, so how come this arrow didn't butt down into the 0, 0? I don't know, I drew it late at night, that's what happens. But we can see that the green and the red are kind of similar-ish, and the blue is kind of longer and pointing elsewhere-ish. So we already have a notion that vectors are not all the same. And we could look at the ends of the vectors, but we'll talk about this a little more. A vector really is a data type, because not only does it contain numbers, those numbers live together. And if they live together, they work together. In other words, we don't want to say, oh, I'm looking at part of a vector. No, there is no part of a vector. If you're just focusing on a snippet of a vector, then that's a smaller vector you're looking at. But it's not the big vector. The vector represents a set of scalars that work together. Now we know how to deal with scalars, right? Numbers, bytes, bits. They're numbers, and we can add a number, we can subtract a number. If we subtract one from the other, we kind of get a distance between them. If we see that they overlay exactly bit by bit, we say, well, they're equal, right? If we subtract them from one another and it's a big number, we say, oh, they're far. If I put them one next to each other, I say, whoa, that's out of order. I can compare them. Well, we want to do the same thing with vectors. We want to be able to take two vectors and treat them as if they're scalar, except they're not. So we had to do some math in order to provide these very operations. And this is where vector math comes in and my mind checks out, because I don't do the math by hand. I defer to the computer and pre-provided functions to do the work for me. So how do I compare an n-dimensional array? How do I compare a two-dimensional array? I have 2 points. I want to know that they're closer or further away. I want to know that one of those vectors is bigger than the other. If I just plotted 2 places, 2 vectors, which one is bigger than the other? How do I sort them? So for vectors, we can consider several questions. Are they the same length, meaning distance from the origin, or from their axis to the point that the number represents? How far along the x, how far along the y, some combination thereof. Are they the same angle? Are they pointing at the same thing? Do they reach the same point? Could they be coming from different origin, but essentially ending at the same point? If they end at the same point in that n-dimensional space, I could consider them somewhat similar or equal. And then if they don't actually point in the same direction or the same exact, what is the distance of them? And I can say what's the endpoint distance, or what's the line distance between the 2 lines, and so forth. So these are various math things, and it turns out that in order to compute that exactly, there's a formula, you know, and you can take the sigma for I to n across all dimensions, and every element compare, do the square, the sum of squares and the square root of and all of that, and add it up together, and you get a result. And that's the math, which we're not going to do today. But the important thing is that there are roughly 3 different ways in which we typically compare vectors. And those turn out to be important when you're doing vector search, because you'll have to tell your index, how are you computing the distance between vectors? The first one is Euclidean. Euclidean is the simplest one of them, because Euclid is ancient, so I guess it's simple. I don't know. But it just compares the ends of the vector, roughly speaking. So it says if the 2 points it ends up at are close, then it's close, and far is far. How did we get there? What path along the way? Doesn't matter. Just that. That seems to be the least popular and least useful one in in practice. The second one is comparing angles. That's called cosine similarity. Cosine similarity is massively popular. It has a cousin that's even better, but it is more popular. Not because it's prettier, but because it costs a little less to compute. And if you have vectors that are pre-normalized, namely that all of the numbers there are already shrunk to be in the range of 0 to 1, then cosine similarity produces the exact same measure as dot product, the better cousin that I'm going to have on the next slide that I haven't mentioned yet, but you already know. That was a joke. Usually people laugh, but okay. I understand. The person before me was very dynamic. I don't compare. I vector compare. Fine. So that's that. That's comparing cosine similarity. And then dot product really is a little more of a combination of the distances along normalization in their own dimension that comes together. Dot product is better. I had to go to third dimension because it's visualizable, but as a concept, the dot product lets you compare things in the right scale, whereas cosine in there would have gotten lost on just trying to plot a combined angle of all dimensions. Dot product does those dimension by dimension and therefore gives you more accurate normalized measurement. So dot product, the cost of dot product is just computational, that if I do that, it costs a little more to compute. But for all intensive purposes, that is the best you can do to compare. All right. So if I had to do that math, and I already told you that Euclidean is really, really easy, but doesn't give you good results, you're like, I don't want that one. And then you have cosine, and it's like, yeah, that's good for as long as I can, get the accuracy right. Maybe I pre-normalize the vectors. And then you have dot product, which works really well. I mean, eventually, all of the machineries, all vector indexes, whether you're using pgvector, whether you're using Oracle, whether you're using, MongoDB and Atlas vector search, whether you're using Azure Cosmos DB, all of those indices, or Elastic has a vector index now, all of these indexes are trying to do something. They're trying to cut down the amount of comparisons you're doing in real time. Because that math I showed you, the little sigma with a 1 to n, well, when you have an n-dimensional vector and its n is 1,000, that means for every vector, I have to do mathy stuff 1,000 times for 1,000 elements. That's costly. That's like really going to heat the room with the CPUs. So vector indexes try to lower the number of vector comparisons I'm going to do. Whatever comparison method I choose, it's just trying to lower it. And there we have it. That's what vector indices do. They are arranging all of the vectors we fed them in such a way, index, that I can enter with a vector, my query, and do less comparisons around them. Now, some vector indices, there's also a structured, I forget what the acronym is, maybe somebody can tell me, but there's a disk-based ANN, and the disk-based ANN basically says, well, we'll store similar vectors in the similar location in space in blocks on file, and then when you come in with a query, we'll just go to that one file and read those and just do those. Others do it in memory and all kinds of tree-ish and hierarchical tree fashion, but all of them cut the problem in order to reduce computation. So this is why we're talking about efficiency at scale. When we have a search application, not the, oh, I talked to the chatbot once, but a million concurrent, we want a structure that can do this again and again and again, multiple threads, just burn CPU and give me the answer as quick as possible. It's not physically feasible to just scan all of the records I have, all of the vectors, right? And these vectors are going to contain information. They're made somehow, and we'll talk a little more about that, but those vectors represent your data, right? It's like I took from my ontology, from my documents, from my PDFs, all of the important words for the law firm, and I made index on the important words kind of thing, right? That's what we're trying to do. We're trying to create a search experience where information was encoded into vectors, and then we come in and say, oh, I have a question for my database, and those vectors represent my data, and I'm going to compare my query vector against those pre-stored vectors and tell who's the closest, and that's going to be the most relevant one. That's what we're trying to do. This is why, if some of us may have remember from math, there's this thing called KNN, K nearest neighbors, which is a very precise algorithm. I do the sum of squares, and I find the point that's closer to all the other points in the cluster. Here you see on slide A and N. A stands for approximate. We're willing to lose something, approximate. We're willing to lose some accuracy for the sake of speed and efficiency. Because we're in database land now, we need to answer things quickly. If we want absolute accuracy, we could. We could compute K and N against every vector and get a more precise answer. Turns out A and N, good enough. You lose so much on other things that little lossy thing is a good sacrifice to have. All right. So a vector index is nothing but a data structure that contains a whole bunch of vectors in such a way that when you come in with a vector, it knows where the nearest ones already is. You don't have to scan them all. And there are some, because we use it in database and stuff like that, that we may say, hey, I indexed a whole bunch of data about my customers. I also want to say a period of time. Well, periods of times are not part of a vector. They're not part of the context. They're just extra filters. So there are also hybrid indices that are capable of pre-filtering from the universe of 1 billion to, say, your 10 million, so that then when you go in with vector search, it's even less work. So that's what hybrid indices are. MongoDB Atlas has one of those things. I don't really know about the ecosystem well enough to tell you which other vendors have it, but it exists. Okay, so I implied that vectors are somewhat superior or give you a better effect or are useful, and I didn't talk about why and what that means. So what is the classic search? The classic search is keyword search, right? It's the old Bayesian formula, taking a keyword and saying that the rank of the search is proportional to the frequency and proportional to the document infrequency. The frequency of my keyword found in the document and the infrequency in all the populations. The more it is on both axes, the better the match is. Even that is too much math. Initially, Google didn't even do that. Initially, Google just counted words. They said, here's a document, take each word. If the term query appeared in this document, yeah, you probably want it, right? Which means that if I was talking about a mouse, I would get Little Mouse in the House books. And if I was talking about mice, it was not clear whether I'm looking for vermin or for pointing devices, because it's just a keyword. It means nothing. It's just a keyword. If there's a hit, great. If not, not. Semantic search is this thing that says, well, wait a minute. When I'm typing in mouse or mice or whatever it is, I'm actually looking for a concept. I have in my mind a semantic meaning around this, and I want the computer to bring back something that is semantically related to my query, beyond just matching words. And it turns out that using vector search for this purpose is superior to trying to do all the tricks we could with traditional keyword search. As an aside, hide my vendor badge that I don't have. Look, traditional search did really well for 15 years. Like really, like Elasticsearch is wonderful. They have a vector search now, but I'm saying just, you know, Solar, Lucene, all of these things. Phenomenal things we did there with fine-tuning, with synonyms and with stemming and with, you know, all kinds of pipelines and with dynamic boosting and with static boosting. Yes, we made it kind of work, but it still had no idea what we're talking about. No semantic meaning. And vectors really bring us into this area where we're actually understanding what a query is in order to sift through data and bring you the relevant results. So a vector index gives you the idea or the notion that it's performing a semantic search, that it understands your data. With vector indices, we can do image searches. If we can encode images in some way that then vectorize them and then we can vectorize our query and then match those and find I'm looking for a herd of cats or a flock of seagulls, the band or a flock of seagulls, it should bring it back. And generically, it's just doing vector similarity in all cases. In traditional indexes, it's keyword-based. If a keyword is present in the query, it will influence documents. And if all keywords are present, roughly speaking, the document is more relevant. And even if your query spells a notion, if a keyword that appears in a document relates to this notion, it matters none. Only if the query keywords are present in the document in one shape or form. And we can't really use that in images because we type in queries in English and images are pixels. So it wasn't really useful for image searches. And it has limits on similarity because unless the person was generous enough to put in a whole bunch of keywords, it's likely that they missed stuff because the document exact composition was with other words that you just didn't type. So it's more difficult to make it relevant. Here's an example. My query is a fine red wine. And let's say the text, the documents are the text in the text column. So if somebody said a great wine, I can see that, oh, the word wine here and here, yay, yippee. So if I did a token search, traditional, then there's a match, right? How much, this is symbolic, don't try to replicate it at home, but this is just to illustrate that this mentioned wine, so okay, great. And maybe a fine was, somebody took the time to work out that a fine and great are the same in a synonym dictionary. Yeah, go do that for all of the English language, right? On your domain, maybe, but no, we didn't do that. So it got kind of a lower score. Whereas semantically, a fine red wine and a great wine are pretty close to each other. You get a higher score. 1 is a high score and 0 is a bad score, or further away, right? Second sentence, this aged like fine wine. Well, semantic search should give this a lower ranking. This query was looking for a fine red wine, and this is a sarcastic comment. But token search would say, oh, look at this, it's fine, and it's wine, and it's wine, and it's higher because I have 2 token matches. So this is really trying to drive home the idea of token versus semantic. Semantic, what I mean. Token, mechanical. And finally, the last one here, none of these words appear here. Semantic search should have learned from its training of whoever generated the embedding. We'll talk about this a bit, that this is a good match. And token search has basically no chance unless somebody really encoded this to be some kind of very particular niche wine nomenclature and did synonyms and boosting and all kinds of stuff like that. All right, onwards. Are we good with token, mechanical, semantic, meaning? Yay, all right. Cool. So how do we encode meaning, though? Yeah, great, there's magic, but I need to hire that magician. How does it work? So, roughly speaking, we take documents, which are input streams. They have a bunch of words, right? So I can imagine my whole document is just a sequence of words. And I'm going to take it and break it into chunks. And chunks are going to be kind of tokens. I'm going to tokenize. That's not too far from what we did with traditional search. We always had tokenizers, except there, tokens represented a discrete element from the input. And here, tokens are broken only in order to find the relationship between them. And then we put it into an embedding model. This is where the magic happens or happened already. Embedding models are the things that are able to take my language, my words, my word salad, and convert them into a vector. An embedding model is an AI operation, a machine learning operation. It takes the text, builds a neural network, finds all kinds of, weights and biases to the formulas of the neural network, and as a result, a vector for two similar concepts, both vectors will be close to each other. And a vector generated from a good embedding model for two dissimilar will end up far apart. So all of the magic really doesn't happen in the vector search or the ANN or anything like that. It happens here. Somebody trained an embedding model to be able to convert your image or your text or your image and text, hybrid models. Somebody took the time and expense necessary to build a machinery that you feed it text one way and it comes out with a vector the other side. I'm not going to talk about how to build those because I don't know. But there are Python libraries for it, and certainly it's a worthwhile endeavor to learn about them for your particular use. There are differences between them. They produce different qualities. I wouldn't say one is universally superior. I would tell you that just working with different embedding models recently, the vectors were such that it was very apparent without having to do too much work that using one for the vector generation and search and another produced very different results in terms of retrieval. So my advice, undocumented here, is try different ones. If you're going to run your data set through an embedding model, try different embedding models for your use case, and you'll be surprised how different they are, even though they're all quality. Yes, sir?
Isn't the embedding model dependent on the model that you're adding to?
So the question is, isn't the embedding model dependent or related to the model that you're using? I'm assuming the model that you're using means the LLM in the RAG architecture, and the answer is absolutely not. Meaning that the embedding model on its own is based on some linguistics and training and labeling and stuff that somebody went through. But it produces a vector. And all its job in the world, in RAG architecture, that we'll talk about in a minute, is to find documents relevant to the query. But it doesn't answer the query. It just says, I want to map similar concepts to the same dimensional space and further concepts to different places in that same space. That's all it does, for the purpose of that then when I go to take a random concept, I can map it into space and say, hey, what's around there? And it will find similar stuff because it's in the same space area, and further things in space will not appear relevant. It's all it does. It's just pure mechanics. So there's an input stream, that's your data. There's an embedding model, that's somebody built an embedding model and you borrow it or you pay for it or something, and then it generates a fixed length vector. You stick that in a vector index, and now you have a database of vectors. A database of vectors that knows how, when you bring it a query, to find the most relevant vector to you. And now we're going to retrieval augmented generation. That could be exploited. If I had a question about stuff that ChatGPT was trained last year, how does it know what happened just yesterday? ChatGPT was trained on open data. How does it know the documents in my private database in my company? Doesn't. So what we're going to do is we're going to do some prompt engineering. We use RAG when we want to do semantic search, meaning I want to find relevance, not keyword matching. When I have proprietary knowledge, whether it's because it's temporal, the LLM was trained long ago, or just private data that LLM never knew about. And we want freshness, meaning we don't want to have to retrain the LLM model, which is very costly. I'm talking tens of millions of dollars. So we don't want to retrain it every time a new document entered our intranet, right? We don't want to have to rebuild the whole LLM model for every query or every day. That's very costly. So with no RAG, what I would have done is a user would have asked the LLM a question. Hey, what internal form should I use to ask for a new chair? Return to office questions, right? And then the LLM would have used, whatever it was trained on generically and say, oh, use IRS 4562, depreciation of fixed assets, right? What else does it know? It doesn't know about the procedure at Marklar Corporation. How would it know? So with RAG, what we do, it's a little more complex. The user first asks a question and creates an embedding. So it asks the same question, what internal form should I use for the thing? And it asks the embedding model, not the LLM. Ask the embedding model, hey, given this text, give me an embedding. Remember, previously, I took all documents, all forms in my company, and created embedding for them. So now, I want them to meet. So I take that embedding, that query embedding, the transformation of my words into a vector, and then I take that vector it gave me, and I go to the vector index. And I say, hey, I have this vector. It's no longer English words, it's a vector from the same space, the same very space of all my documents. And I give it to the vector index, and it tells me, here are the things closest to it. So now I have a bunch of documents. How many do I want? I don't know, 1, 2, 3, 10. Your application will determine. But I take that, and I say, ooh, I found some documents that talk about that from my own company. And now I give that to the LLM. And I take the original text that the user asked. What form should I use for? And I say, hey, the user asked, what form should I use? And I found these documents that seem relevant, A, B, C, D, content. And I tell the LLM, hey, can you summarize it for me, please? So I do prompt engineering. Really, RAG is prompt engineering pipeline. It takes a user query, goes on a side tour to vectorize it, go to the vector search, find relevant documents, and says, given those documents and the user query, please answer me. LLMs are good at that. They can read stuff, summarize it, seem to be reasoning with it, but now it's grounded. It has context that is fresh from my internal database. So it gives me relevant results. Are we good with this so far? Good. Yes, sir. Text. Right. So I'm not sure what the question is, but I'm going to repeat what I understood from what you said. There is a fine line invisible in this picture between the embedding model and the LLM. Two different animals altogether. This might be Ada04, the embedding model, and this might be ChatGPT or Anthropic or, I don't know, Cohere, I don't care. But those are LLM models. What do LLM models do? They read text and they give you completions. Internally, if they had vectors within them, I don't know about it, and it's not what this talk is about. I'm assuming This LLM, I consider it my intern that knows English, but has not gone to any other class in the world. Doesn't understand anything except for how to put words together. Not only hasn't it understood anything about the world, it puts words together according to reading all books in the world and just saying, you know what? I saw that this word, world, follows hello in most cases. So if you told me hello and it's go world, that's all it does, really. Embedding models are different. Embedding models are saying, I learned all the text in the world, and it looks to me like this sentence and these sentence are kind of similar, so I'm going to put them in the same spot in n-dimensional space. And therefore, I can ask a vector index, I can compare indices and say, are these related semantically or far away semantically? So it only answers distance questions. Does that answer things? Okay. One more? Yeah. So if I understand the question is, hey, if you're asking a question in English, and there's an embedding of a picture of a cat, how does it fit together? How does it work? So it turns out, to do this kind of trick, you need an embedding model that is a hybrid model. Hybrid model are trained on images and text together in such a way that a picture of a cat and the word cat appear in the same place in space, and a picture of a dog and a word dog appear here. Therefore, when I generate a embedding from text from the query, hey, where's Fido? It will go towards the space where the dog is, which includes a picture or a word because it's a concept. Great question. Yes, one more. I'll try to translate what you asked into my next sentences, and I don't know if I'm going to answer it, but you see this? Is there a dog in here? No. A dog. There's no dog here. There's no cat there. Right. All we know is that given an input cat or an input cat picture, that there will be a vector drawn in 3D space. And a big cat or a lion will also kind of end up in that location in 3D space. We never say, hey, I found you, now draw me a cat. That's not its job. Its job is just to say, I'm storing the whole space, and there's points in which things exist, and if I give you something, it says, what are the vectors that exist around me? Now, those vectors I tie in my database, I just say, hey, this is for document A, or for picture 123, or for something. So when I pick that vector, I can go back to my documents and say, he found that thing. That is related but in space, so that's probably what I was looking for. But which one you pick that being close together is going to depend on which of those metrics. Correct. Correct. So if the question is, so do the embedding models have a notion of I'm an embedding model for cosine versus I'm an embedding model for this? I thought yes, and somebody told me no, and I'm still looking for that answer. If anybody knows mathematically, I'd love to learn. All right, one more, and I'm going to push on, and I'm going to take as many questions as fit until 6 o'clock. Yes? So I think the gentleman before just asked, hey, does it matter that it was using distance functions based on cosine calculation versus dot product or Euclidean? So do I have to use an embedding model? Do I have to do distance searching with the same method that the training was done? That was the question, I think. So if I took everything you said as true, how does that answer the question? Do I then have to use the same distancing method of, say, hey, I'm using the same embedding model to compare in the embedding, but am I telling it to do a Euclidean cosine or so I think you are still saying, which was my initial intuition, that you need to do vector comparison. The same vector comparison method I use was the one used in training. Because there are embedding models that are called, you know, Anthropic V13 underscore cos. So it seems to me intuitively that it would matter, but then somebody told me it doesn't, and I'm just not math strong enough to know. So let's push on. An interesting conversation. Let's maybe carry it forward and just move on to other topics here. And I want to know an answer. So if anybody finds the truth, please let me know. All right, so vector engineering, these are SCaLE, this is RAG, which is glorified prompt engineering. So when somebody says, hey, do you know RAG? Tell them, yes, it's glorified prompt engineering. You take a dumb LLM that doesn't know your stuff, you do vector search to find stuff you know, and you tell the LLM, here's what you know, and now answer this. Boom. Whoa. Getting there. But not just text. Embedding can create it for non-textual data. I can create it for images, and the gentleman in the previous session talked about that for a bit. I can create it for sound. I can take sound waves and convert them. And one interesting application I saw was they're taking recordings of engines that are humming well and engines that are not. And by doing that, they were able to see if somebody's starting to hum not, record the engine right now, look at the database and say, oh, you have a loose piston number 3. That's nice, right? I don't have to go to LLM. Vector indices are useful on their own. If I can encode the data and I have more than one dimension, vector might be for you. If I am operating an online dating site and I have various factors, maybe age, maybe location, maybe, I don't know, preferences of all kinds, I can take each one as a dimension, find a way to encode it, create a vector, and use vector search. Because will I go out of my way for somebody who's more compatible or a little closer for somebody less compatible? Like, right? I can take binary data of various, opaqueness, which includes operational metrics, which includes random buffers and random snippets of transaction streams that may or may not contain transactional financial data that is fraud. I don't know. If you can create a signature for it, if you can extract elements and encode them in some way and train on that and say, this is a sign of goodness and this is not, or this is similar to others and this is further apart, then, you can go crazy, go wild, encode your own thing. Those embedding models for English, yeah, millions of dollars, a lot of research, a lot of manual labeling work. But you probably have in your company or in your project things that you can vectorize. And you can use these same techniques and the already existing infrastructure to encode them and then use them for your relevance. So the question is the expensive part is to figure out how to vectorize them. Potentially. Maybe your knowledge of the domain or the domain lends itself to it. And, you know, like sound waves, quantization has been known. Fast Fourier transforms, you know, transform frequencies into, yeah, X, Y. I mean, there's all kinds of ways. It's probably been done. The science to put all of this together has come together and gotten into focus, but the math behind it, we're not inventing new math. We're using it. Yeah. I do like this image. I don't know why it's kind of, I want a screensaver like that. I don't know. And then, so we can use vector search outside of the context of RAG, is my main message. And we have that problem even on things that seem mundanely like, oh my God, I need to look through things. So, okay, so let's know what those categories. I want a drop-down of age, a drop-down of gender, a drop-down of this, a preference of whatever. And it's like, you don't have to. If you can find a way to encode it, you might be able to vectorize it and give a much more nuanced, blended response. And hybrid, we talked about images and text together, so hybriding is also possible. This kind of concludes this is kind of how it works and how to reason with it and why vector search and this. So now I'm moving to ecosystem. Where can I find it in the wild? Do I have to use ChromaDB like all the Python methods show, things like that? And the answer is no, by the way. But yes, if you like Chroma and it works for you. So major players, Microsoft. Azure has Azure AI Search. So it's a packaged product you can address or service. Cosmos DB has a vector index in it. So if you're a user of Cosmos, you can throw a index on data in Cosmos and thereby gain operational efficiency for not having to maintain multiple places. And the Azure database for Postgres also supports vector search because Postgres supports vector search and it supports the extension pgvector. Simple enough, right? SQL Server, however, on its own does not have a vector index. It recently gained vector operator. So it recently gained a linguistic vector addressing a vector data type. So you can declare a column of type vector, therefore you could store it there instead of a var binary or var char something. But it didn't understand vectoriness. It couldn't compare two vectors and say, are they far, or what is the distance between 0 to 1 or something. Now, there is a data type, and there's also a function, a SQL function extension, that is called, you know, distance, parentheses, vector A, vector B. Therefore, you can do the math there with no efficiency, with no vector efficiency. So, SQL Server, getting there, the other options exist. In the NoSQL world, Redis has a vector index, so you can do that. It's nice. It always had an array data type, so that's kind of what you use for a vector representation anyway. But Redis is not a transactional database in my book. So, I don't know. It's a NoSQL. I wouldn't quite call it a database. MongoDB Atlas has Atlas Vector Search. It's hybrid with their textual search and also with extra filters. So for very large scale, like you have a huge data set, that thing rocks. I like using that. Elastic has an index, has a database type, has a search engine data type for your field called dense vector, so it has it built in these days. And Elastic is interesting because traditionally it was a keyword search machinery, and now it has both possibilities. So if that's your data store, yeah, you're in luck. Atlas also has text search very similar to Elastic, so that's also possible there. Sorry, one sec. AWS Document DB, a NoSQL thingy-mabob, has an index, and Pinecone has a vector DB as a service. Pinecone is unique in the fact that it is not exactly cloud resident with a major hypervisor. It's its own thing, so you're always calling out and in of it. But, you know, solid, good implementation, commercial support, all that jazz. In the RDBMS world, Postgres has PG Vector, very popular. There's two flavors, by the way, in there. There is the ANN, which is a more memory fast at runtime thing, but takes longer to build, meaning that when you index, when you add documents into your, or rows into your database, it's more heavy to build up. So if you have fast-changing documents, that costs you something. It also has a disk-based, I forget what the acronym, but the disk-based ANN is very fast to build but slow to query. So it kind of depends on, are you really changing your data really fast or querying it really fast? You might play with it. Oracle has an in-memory neighbor graph HNSW. HNSW, hierarchical neighborhood, small world. No, hierarchical near software wonderful. It's an acronym that I can never pronounce. But HNSW is that thing you want. It's basically a tree structure that takes a vector, says, oh, you look like you're kind of in a category of these four, and within these four, it's like, oh, you're kind of category of this 8 and this 16 and and it drills, and when you get to the bottom leaf of there, you end up with just enough vectors for you to do the actual comparison. So that's the fast way. And then the IVF inverted file, that's the slow to read but fast to build. Oracle also has it as an external file, and Oracle being its Oracle-ness, that they manage it for you. MariaDB has a vector index, so that would be closer to the MySQL world, I guess. And SQL Server, pending, not quite there. By no means is this comprehensive, and if I made a mistake or by now, because this slide is 6 months old, there's more, I'd love to learn about it. So back to the original question, which is vector search right for me? Well, I don't know. I hope you learned enough to make up your own decision. So what should I look at? What should I ask myself to answer the question, is vector search right for me? The first one, foremost, is the effect. Will employing a vector search machinery give me a better result than I can get otherwise? Not just cost, just like, hey, is it giving me what I want? If it's not giving you what you want, don't do it. Can I retrain the model? All things considered, if you're considering, when you're considering RAG implementation, RAG is good when you have the constraints that prevent you from retraining your LLM. If I could take the context, my documents about procurement of a new chair, and train ChatGPT and say, hey, by the way, I also have this. Know everything about my company, and now I can just directly ask the LLM. That's better. That's more efficient. Probably going to give you better answers than what's called a one-shot approach that RAG is. It's a one-shot because I take my context and my query and submit it at once. It's not a conversation. So that's something you want to look at. It could be that your data addition is slow and retraining or fine-tuning a base model is worth it. So if it's possible, you might want to look at it. Should you use a hybrid index or two indices? So a hybrid index, yay, absolutely. Two indices, like have one for keyword search and one for vector search. Bring the results from both and maybe evaluate which one is better at runtime. Maybe employ both. and have two result streams so people can judge and then let the best one win? I don't know. These are kind of UX questions. And also you want to kind of ask yourself how much control you want over this. So I mentioned in the beginning that different embedding models will yield different results. Therefore, you will have to probably evaluate a few. You also want to see, do I have personnel in my team that will take it on and really understand how it works? What do you do when these things don't bring great results? What knobs can you turn? So if you're taking a pre-composed solution from a vendor and there's not a lot of knobs to turn, you're stuck with what it gives you. If there's a lot of knobs to turn but you don't know what they're doing, well, that's just chaos, right? So you want to think about those things as you say, oh, let's adopt this. It's not going to be as smooth sailing as the Jupyter Notebook tells you. It's just not going to work that well. And you're going to have to really think about how do you tell that you've arrived. So model evaluation, basically, saying, hey, I got a result set. Is this good? Did it bring me the relevant documents? How much data cleaning do I need to do before I vectorize my documents? I have a client that has some CRM, and one of the issues is that a lot of the entries in there are mail chains with re. And the question is, do you take the whole thing as a chunk, or you want to break it into chunks, which is meaning unwinding recursively of all of the email chain, deduplicating against messages, because like, hello, hello, you know, it's like just repeating data. So doing that kind of work is not something that's done automatically for you. It's things you'll have to deal with in the real world. Taking a 20,000-foot view, I'm really impressed by how AI, LLM, and things like that kind of ate everybody's R&D lunch. It's been massively popular. I'm kind of glad that chat is like, okay, I don't want to chat with a bot anymore, but RAG is still very relevant, I think, and retrieval of data is still going to be around forever. You have data, you want to access it, which one do you want? That's what retrieval is. So this is great. We're still in very early stage. Those knobs are not quite there and not quite well labeled, so people are trying to figure out, hey, I have some stuff, but I want to promote this product. How do I promote a product in a RAG world? Embedding was already done. There's no like, oh, I'll boost every element in the array by 3 to make it more relevant. If you change the array, you change location in space, it's no longer relevant. So how do you do these things? How do we do static boosting, dynamic boosting? Still a strong question that is not well answered. Limited tuning there. And the expertise skill gap is starting to show, right? We all have FOMO. It's like, oh, Steve discovered how to do all this stuff. Oh my God, I'm falling behind. And Steve's like, I don't know, I just used, you know, the Jupyter notebook that I got as a sample. So I think it's very worth while experimenting with, getting into, playing with a few models of embedding and vector searches, seeing the results come back. It's very good experience, and it's eye-opening. You might never actually put it in production, but understanding how that thing works can make you better in your information retrieval endeavor. I truly believe that. This is my thank you. I think we're kind of out of time. Yeah, 1 minute. Huh? Okay, so there's a couple of minutes for questions. Yes, sir. Oh, I want to mention on the mic, because I can speak loudly, that there's going to be a birds of a feather about search and vector search happening at Salon.
Right around the corner in the Postgres room, and happens at 30 minutes. Anybody who's interested in search, vector search, or analytics, I don't know what I have to inform you about.
Yeah.
Vector search It's only vector search, the semantic search, or Lucene query can also be used for semantic search.
I would say only, so semantic search is a marketing term put on top of the mechanics of vector search. I don't think you can say, oh, traditional keyword search is semantic because it's so mechanically tied to the appearance or non-appearance of a token. So it doesn't have this notion of semantic meaning. It only has a notion of mechanical find, don't find, and add a score of how many of the token actually exactly matched. So it doesn't do a thing like distance. So, so I would say semantic search is the marketing term bolted on top of vector search. Vector search mechanics have to do with vectors. Vectors are produced by embedding models.
Got it, thank you.
Question in the back there? I can barely hear you, sorry. Okay, yeah, that's a good question. It's a very interesting thing to me. So embedding models have a token limit. They like say, okay, I can encode up to this much text. Well, what happens when your PDF or book is much longer? Well, you have to chop it down. But even if you don't, if you have an email, you could say, I'll index the email under the theory that the semantic meaning of the query coming in and searching through the email for, you know, when did Steve talk about, I don't know, naps, that it appears somewhere in the email. But it could be that you want to chunk it still by paragraphs and index each paragraph separately under the theory that this relevance is paragraph bound, which is kind of true most of the time. So a lot of time people take PDFs and instead of indexing the whole PDF as a unit, they take chunks of it, paragraphs, pages, something, chapter, book, verse, whatever, right? Break it down further under the theory that the query will be about a certain thing. And then when you retrieve it, you can say, ah, it's paragraph 10. Let me also pull paragraph 9 and 11 just to be a little more window context for the LLM, but that's good enough. I don't want to bother you with, you know, it was a best of time and the worst of time and all of that. Like, just tell me when Jean Valjean goes to jail. Sorry, that is a, yeah. Anyway, you get the picture. So chunking is very important. When you're doing chunking, here's a freebie. Add your metadata from the whole document. Meaning that if I have an email from Nuri to Steve about Jean Valjean, blah, 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 then you take that metadata of when the email's from, blah, whatever you decide is important, and you slap it into every paragraph to be indexed. That way it has relevant in the context of the envelope, plus the very hyper-focused paragraph. And that, to me, in my experiments, that worked the best. Yeah. So the question is, have you thought of or implemented security into things because different people might access the same data but don't have the same access permissions or security clearance level or something? My answer to you is, I've never done it. My intuition would tell me that what you would do is you would create multiple indices so that I don't accidentally bring context around that could hint at what's in there. So I would create different, I would just spray out the data to different stores that are according to access level, and I wouldn't mix them in any way. A vector itself doesn't embed a security or non-security. I don't think you want that. Well, then they divulge something if they said so. So exactly, so that's why I'm saying I wouldn't want to get into a situation where I was near enough in space to something to come back and divulge the fact that somebody above me can see that I can't, even if I somehow manage to snip it. But that's the same with any kind of I would agree. But yeah, I don't have specific implementation experience with that. Okay, thank you very much.
Sorry. Can we have a round of applause for our presenter, please?